بالمناسبة. Halo, tes. Sudah dimulai belum ini ya?
Assalamualaikum Bu Riris. Siapa saja
Ya.
nih Kak?
Waalaikumsalam Bu Fatma.
Oke.
Ya,
Backgroundnya ya.
we
Jadi gelap.
are going to start our webinar.
Ya saya gelap ya ininya. Ini kok terang kalau Bu Riris sama Mbak Alfian ininya.
Because of our
Cahayanya belum dari depan.
Oh, berarti
Iya,
perlu
iya.
lampu nih di depan ini.
Ya.
Iya Bu.
Kalau zoom kuncinya bukan ruangannya yang terang, tapi cahaya dari depannya.
Cahayanya ya.
Ya, ngadep jendela atau dikasih lampu depannya. Ruangannya gelap enggak masalah.
Iya.
Ini saya suka pemilihan backgroundnya ini. Pemilihan background itu kalau bisa ya yang agak dumi apa gelap.
Mana ini banyak hiasan nih di belakang ini.
Ya, biasanya dari kameranya, Bu.
Iya.
Bu Fat.
Gimana?
Ini APL-nya sedang saya proses. Jadi nanti segera saya kirim ya.
Siap. Nanti sore bisa rapat kan?
Bisa, karena saya kan ini sampai jam berapa toh webinar ini Bu Riris?
Sampai jam 11
ya?
Pak. Iya.
Ya, jam 11 jadi bisa.
Rapatnya nanti.
Iya, jam 3 kan bisa saya. Pak Alfian.
Orang, Pak?
Saya yang dari saya 14, yang dari Pak Yasin saya belum tahu. Saya agak saya agak ngirit dulu karena nanti kalau tak habiskan semua tahun depan menggos nyari tambahannya.
Tidak apa-apa. Ini teman-teman tak kerahkan juga, Bu Cici teman-temannya tak kerahkan.
Ya, Bu Cici kan juga baru pulang jadi. Pak Alfian, lamarnya nggak ngobrol sama Pak Alfian. Di rumah ya Mas Alfian?
Di kos ini Pak.
Di kos?
Sudah
datang ke Surabaya ya?
Ngurusi seminar itu Pak.
Seminar yang
iya Icoston itu. FSP.
Oh, yang fakultas itu.
Iya.
Oh iya. Jadi sudah ke Surabaya ya. Mulai kapan Mas Alfian ke Surabaya?
Hari Minggu kemarin Pak.
Oh iya, ya ini. Mudah-mudahan ini yang masalah HBM. Oh ini saya kok malah jadi nurut ngobrol di sini ya.
Iya.
Nggak, saya sampaikan sebentar aja. Ya tinggal the last stage lah ya. Artinya konfirmasi dari para corresponding author. Kalau itu bisa segera ya AIP akan segera mempublish. Insya Allah urutannya kita tidak terlalu panjang karena itu kemarin ada masalah dengan Pak Gunawan karena nggak ganti email ke STMM itu ternyata sudah clear. Jadi dikontak langsung ke AIP sama yang bersangkutan. Saya takut kalau saya yang kontak nanti antrian kita jadi mundur. Berarti kan kita harus ngubah lagi tuh ke list Excel yang kita kirim ya Mas Alfian ya.
Iya Pak.
Tapi ternyata kemarin bisa kayak shortcut gitu. Langsung dikirim, jadi langsung dikirim email baru. Jadi mereka langsung membetulkan di belakang layar. Karena kalau membetulkannya by system kita harus upload baru lagi, antriannya akan mundur lagi. Ya udah gitu aja update-nya Mas Alfian. Terima kasih bantuannya selama sebelum sampai dengan saat ini. Setelah ini saya tadi juga sudah menyampaikan ke beberapa reviewer eksternal terkait ISPIAM yang sudah selesai kita kerjakan. Dan tinggal sertifikatnya ya. Kan belum dikasih itu sama Mas Rohman. Semua reviewers itu belum dikirimi.
Ya, mungkin dimulai saja Bu Osma barangkali.
Oke, monggo.
Biar on time.
Ya sudah 45 sudah 7:45. Monggo Bu Riris.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. My name is Osmalina. On behalf of Faculty of Science and Technology, Universitas Airlangga, we would like to welcome you to the webinar Big Data and Artificial Intelligence in the Future of Medical Technology. We would like to extend very special thank you to Rector of Universitas Airlangga, Dean Faculty of Science and Technology Universitas Airlangga, Dr. Leo Antonelli, MD MPH from Massachusetts Institute of Technology, United States of America, Mr. J. Williams, PhD, from National Cheng Kung University, Taiwan, Dr. Rifai Chai from Swinburne University of Technology, Australia, lecturer from Universitas Airlangga and from other university, and lastly, all the participants in this today event. Ladies and gentlemen, at this time we ask you that you all please rise for playing Indonesia Raya and Universitas Airlangga Hymn. Di timur Jawa, Dipa, megah engkau bertahta, Satria Airlangga, Kusuma Negara. Dari engkau ku dapat budaya pusaka Airlangga di permata Indonesia Raya. Bagimu alma mater, ku berjanji setia, berdharma bakti suci, berjasa mulia. Belajar untuk Nusa
Ya.
Hiduplah air langga, tetap kau jaya.
Thank you. You may please be seated. Without further ado, I would like to invite the Vice Dean of Faculty of Science and Technology, Universitas Airlangga, to give a welcoming speech. Ladies and gentlemen, please welcome Dr. Fatmawati MSI, Vice Dean of the Faculty of Science and Technology, Universitas Airlangga.
Okay. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Dear distinguished speaker, ladies and gentlemen, first of all, I would like to express my gratitude to all of the participants and distinguished guests for their contribution for the webinar Big Data and Artificial Intelligence in the Future of Medical Technology. I hope that all of the participants here will find a lot of experience and knowledge and the rapid advancement of medical technology based on big data and artificial intelligence. I would like to express my sincere appreciation and gratitude to the keynote speakers with their commendable effort in sharing their knowledge to all of the participants as well for their participation in making this webinar successful. I also thank the participants from other universities and institutions that I could not mention here one by one. In order to maintain university rank as 500 world-class university, Universitas Airlangga held several international webinars such as today that is organized by Department of Physics, Universitas Airlangga. By this webinar, I hope our collaboration can be continued, especially in education, research, and community service, because collaboration is an essential component for us to move forward to face the global challenges of becoming a world-class university. Finally, I would like to wish the webinar have a great success. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. Thank you, Dr. Fatmawati MSI. Well, ladies and gentlemen, moving right along to the core of today's event, it is my pleasure to introduce our first moderator, Dr. Iris Lunaling Tias, MT. Dr. Iris is a lecturer in Biomedical Engineering Program, Department of Physics, Faculty of Science and Technology, Universitas Airlangga. Please join me in welcoming Dr. Iris Lunaling Tias, MT.
Yeah, thank you, Miss Osma. Our honorable third vice dean of the Faculty of Science and Technology, and our honorable for the all participant today. Beside from the Universitas Airlangga, this webinar is the participant is from other universities too, that split from other cities in Indonesia. Beside that is comes from other overseas university like UTM, NCKU, and Kobe University. So we still waiting for Dr. Leo Anthony Sali here that I already contact him. So wait a minute for the participant. We still waiting for the Dr. Leo.
Saya izin mohon live nggih, Bu Riris.
Iya,
Semoga
Bu
sukses
Farna.
nggih.
Ya,
Ya,
terima
soalnya
kasih banyak
pada
Bu Osma.
kegiatan lain. Matur nuwun semuanya. Assalamualaikum.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, while we waiting for Dr. Leo, uh, I want to read about the Dr. Leo Anthony Sally CV first. Our first speaker here, he is from Massachusetts Institute of Technology, USA, Dr. Leo Anthony Sally, MD, MPH. Dr. Leo is a clinical research director and principal research scientist at the MIT Laboratory for Computational Physiology, and as a practicing intensive care unit ICU physician at the Beth Israel Deaconess Medical Center. And beside that, he also becoming associate professor of medicine in Harvard Medical School. Dr. Leo brings together a clinician and data scientist to support research using data routinely collected in the process of care. His group builds and maintains the publicly available medical information mart for intensive care, MIMIC database, and the Philips MIT EICU collaborative research database with more than 15,000 users from around the world. The MIMIC3 paper has been cited more than 1,800 times since 2016. In addition, Dr. Leo is of the course directors for Global Health Informatics to improve quality of care and collaborative data science in medicine, both at MIT. He also an editor of the textbook of its course, both released under an open access license. These textbooks with the title Secondary Analysis of Electronic Health Records has been downloaded more than 800,000 times and has been translated to Mandarin, Spanish, and Korean. Dr. Liu has spoken in more than 35 countries across 6 continents about the value of data and learning in health system. His publication have been cited more than 6,000 times since 2016. So I think it's a very amazing achievement from Dr. Leo Anthony Sally. So okay, I will check for the attendance of Dr. Leo. Yeah, okay, ladies and gentlemen, while we waiting for Dr. Liu Anthony, so we will turn on our video profile of Universitas Airlangga. Please enjoy our time here.
There are 165 different programs consisting 39 bachelors, 45 masters, 13 doctorate, 3 4 years vocationals, and 17 3 years vocationals.
41 specialists and 7 professional educations. Among them, there are 5 international class and dual degree programs, and also 12 multidisciplinary programs in our postgraduate school.
Want to know our international class and dual degree program? Here we have medicine, dental medicine, veterinary medicine, pharmacist education, and psychology.
But worry not, there won't be any difficulties, for 2,600 of our staff are ready to assist you at any turn of your study.
And almost 2,000 lecturers to answer your scientific questions, and 224 professors for more difficult ones. Or your answers could be anywhere among 118,000 collections in our library.
And if you wonder, are we always mysterious?
No, we have 39 student clubs, with 10 different sports, 8 martial arts, 5 religious clubs, 7 creative and traditional arts, and 7 more others.
Above all, since 1954, we are proud of our students. In 2017 alone, 444 of them are getting achievements in national and international level. Collaborating with 149 universities across the globe, we are ready, marching with the rest of the world, cultivating the brightest future of all.
Okay, thank you, Mr. Alfian. Okay, I want to greet Dr. Leo. Hello, Dr. Leo. You already enter our Zoom?
Yes, I'm here. Good morning.
Oh, okay. Thank you very much. I'm afraid if you are the wrong date to enter our webinar.
It was a wrong date. I thought it was tomorrow.
US. Yeah, I'm sorry about that, Dr. Leo. So, thank you very much, Dr. Leo. Okay, I start again to start our webinar. Very good morning, everyone. A warm greeting from Universitas Airlangga, Surabaya, Indonesia. I'm very pleased to become moderator here. Thank you for joining our webinar. We have excellent speakers in our webinar event today. Now, I would like to introduce our first speaker. He is from Massachusetts Institute of Technology, USA. Please welcome Dr. Leo Anthony Selly, MD, MPH. Okay, hello, Dr. Leo. Good evening.
Hello.
Yeah.
Good morning
okay,
to
very
everyone.
Good, yeah, morning. Dr. Leo is a clinical research director and principal research scientist at the MIT Laboratory for Computational Physiology and as a practicing intensive care unit ICU physician at the Beth Israel Deaconess Medical Center. Beside that, he also associate professor of medicine in Harvard Medical School. Dr. Leo brings together clinicians and data scientists to support research using that data routinely collected in the process of care. His group builds and maintains to the publicly available medical information map for intensive care MIMIC database and the Philips MIT EICU collaborative research database with more than 15,000 users from around the world. The MIMIC3 paper has been cited more than 1,800 times since 2016. In addition, Dr. Leo is one of the course directors for Global Health Informatics to improve quality of care and collaborative data science in medicine, both at MIT. He also an editor of the textbook for its course, both released under an open access license. His textbooks with the title Secondary Analysis of Electronic Health Records has been downloaded more than 800,000 times and has been translated to Mandarin, Spanish, and Korean. Dr. Leo has spoken in more than 35 countries across 6 continents about the value of data learning in the health system. His publications have been cited more than 6,000 times since 2015. Wow, it's a very amazing achievement, Dr. Leo, I think. Okay, before we go further, I would like to give a little bit information to the participants. After Dr. Leo presentation, you can ask the question directly to Dr. Leo. You can raise your hand with a click the emoticon reaction on your Zoom panel below, or you can type your question on your chat box and then I will read your question. Okay, without further ado, let's pay our attention to Dr. Leo presentation. To Dr. Leo, the time is yours.
Thank you so much. I apologize for the confusion. It's on my calendar, it's for tomorrow. So I actually have another meeting, but I told them that something came up, so I won't be able to join them. But it's a pleasure to be addressing you all in Indonesia. I've been to Indonesia before. I was born and grew up in the Philippines. I went to medical school at the University of the Philippines, and I would love to be back in Indonesia at some point. So I'm gonna share my slides now, and I'm gonna share my screen. And let me know if you can see my screen. Are you seeing my screen now?
Still blank white.
Oh.
Is this still white appearance, doctor?
Let me stop sharing again, and I'm gonna try that again. Share screen. There you go. How about that?
Yeah, okay, very good.
Okay, the title of my talk is An Awakening in Medicine, the Partnership of Humanity and Intelligent Machines. As given as an introduction, I still practice medicine. I work in the intensive care unit at one of the hospitals here in Boston, but my research is all based at MIT. Before I begin, I would like to disclose information about research funding that our group receives. It's primarily from the US government through the National Institute of Health, as well as several industry partners. I'm gonna begin with this most highly cited study that was published in the New England Journal of Medicine back in 2001. Greet Vandenberg and her colleagues published a study looking at controlling blood sugars among patients who are admitted to the intensive care unit. As I mentioned, the paper is one of the most cited publications in the history of medicine. And subsequently, after this paper was published, intensive care units and hospitals around the world adopted some protocol in the control of blood sugar for patients, not only in the intensive care unit, but also in the hospital, as well as skilled nursing facility. And a billion-dollar industry and workforce around hospital and skilled nursing home glucose monitoring was born. But there is something incredibly wrong with how this unfolded. The research was performed in an intensive care unit in Belgium, and its findings, as we find out much later, is not generalizable to the rest of the world. Indeed, the way medicine is being practiced now is based on research performed in a handful of countries. Medical knowledge is generated and maintained by an exclusive club of experts and then distributed to the rest of the world. For low-income countries, research is deemed a luxury that they could not simply afford. So they practice medicine and provide tests and treatments that may not work for, or worse, may be harming their patients. Another big misconception that exists among the public is the belief that decisions made by healthcare providers like me are based on clinical trials. In reality, as shown by the paper in this slide, only a minority of practice guidelines is based on prospective randomized controlled trials, or RCTs. In the intensive care unit where I work, that fraction is about 9%. The specialty with the highest proportion of randomized controlled trial-based practice is cardiology at 10%. The rest of medicine is in single digits. Despite the reality that most of what we do in medicine is based on what is referred to as evidence-based medicine, there is still a strong pushback from trialists that data science is not good enough to inform practice because it does not establish causation. But again, I repeat, most of what we do now is not based on anything that comes close to a causal study. Even when randomized controlled trials exist, there is a suspicion in the research community that they all produce biased results to a certain degree. As we know, clinical trials involve very complex processes, from randomization to blinding to controlling to implementing treatments to monitoring participants. And each step requires many decisions that bring their own assumptions and degree of bias to the results. In 2012, the Institute of Medicine here in the United States commissioned a group of experts to evaluate more than 300 clinical practice guidelines that are in use in the country. And in a report that followed the review, the conclusion was that for many clinical domains, high-quality evidence is lacking or even non-existent. Often, practice guidelines rely on low-quality evidence or expert opinion. In the United Kingdom, the National Institute for Health and Care Excellence and the British Medical Journal partnered and combed through thousands of treatments that are administered to British patients. What they find is that 50% of treatments have unknown effectiveness. 10% actually have been found to be ineffective or even harmful and yet are in use. Only about 40% have some evidence of effectiveness, not necessarily strong, but at least some level of evidence nonetheless. And indeed, when current standard of care is put to the test, 40% of the time there is discontinuation of the practice. This is a paper where Prasad and company looked at 363 research manuscripts published in the highest impact clinical journal, the New England Journal of Medicine, from 2001 to 2010, evaluating an existing medical practice. And in 40% of the studies, the authors found that the practice was actually ineffective or even harmful, leading to what we call medical reversal or discontinuation of a standard of care. The authors opined that it seems that the medical community does not gather enough evidence before a practice becomes commonplace. This is the biggest paradox in healthcare. On one hand, there is a belief that it takes 17 years for an evidence to find its way to clinical practice. On the other hand, it also seems that tests and treatments get adopted without evidence behind them. Perhaps one of the biggest problems in healthcare, which I alluded to earlier, is the historic omission in research of certain groups, including a lot of low and middle income countries, and also including women and underserved populations. And this has skewed the generation of medical knowledge. For example, one of the most cited studies in the health literature is the Framingham study. That particular data analysis has informed how to take care of patients with stroke, with cardiovascular disease, and other types of conditions. But what is unknown is that the vast majority of patients who were included in the study are white Caucasian males. And not surprisingly, scores that have been generated from data that was produced from this study has not consistently been accurate across the board. For example, even in the United States, the predicted risk of a cardiovascular event, heart attack or stroke, was 20% lower for Black patients when compared to the actual number of events. Doctors not only operate with imperfect knowledge, in addition, they operate with unconscious biases, biases that lead to medical errors. Preventable deaths are defined as deaths that arise from medical errors, and these are adverse drug events, hospital-acquired infections, and other treatment injuries. One said that if the airline industry tolerated the error rate that the healthcare industry does, there would be 3 jumbo jet crashes every 2 days. Every year in the United States, upward of 12 million Americans would see a doctor and come away with the wrong diagnosis. Judgment errors account for 86% of these errors, but the rate of medical errors varies by gender and by race. If you're having a stroke, there's a 9% chance that you will have the wrong diagnosis when you go to the emergency department. Being a woman raises that risk by 30%. Health outcomes are also influenced by doctor biases. As demonstrated in this paper, women who develop heart attacks have better outcomes when they get treated by a female cardiologist than when they are treated by a male cardiologist. My first take-home message is that judgment errors in decision-making, including those that arise from biases, is at the heart of medical errors and health disparities. This is true not just in high-income countries. One of the very first papers looking at quality of care in low-income countries was published in 2012. In this paper, the authors reviewed more than 15,000 patient records, which were randomly sampled and analyzed from 26 hospitals in 8 countries. The author's hypothesis was that poor quality of care in low-income countries is due to lack of medications, access to specialist care, laboratory services, and other technology. But what they discovered was surprising. What they found is that after review of the 15,000 records, the 2 biggest contributors to poor quality of care are treatment errors and diagnostic errors. This is another report that is worth highlighting. It came from the World Health Organization, and the report looked at medication use in primary care in low and middle income countries. The authors reviewed 679 studies from 97 countries that were published between 1990 and 2006. What they found was that more than 50% of all medicines in low and middle income countries are prescribed, dispensed, or sold inappropriately. Less than 30% of patients are treated according to some existing clinical guideline. These 2 reports, the report from the British Medical Journal and this report from the World Health Organization, highlight why data and learning have to be at the front and center of healthcare. Putting data and learning at the front and center of healthcare is the mission statement of MIT Critical Data. So our group at MIT, the Laboratory for Computational Physiology, leads this global consortium consisting of healthcare practitioners, so nurses, doctors, pharmacists, computer scientists, engineers, and social scientists who believe that data and learning are the best medicine for population health. We build communities across disciplines to derive knowledge from data that is routinely collected in the process of care in order to understand health and disease better at the local context. These are the two data sets that our group have developed and are maintaining and are offering to the research community. The first one was mentioned earlier. It's MIMIC, which stands for Medical Information Mart for Intensive Care. And this data set has been around for more than a decade. The latest version of this data set is now version 4, and it contains high resolution and multimodal de-identified data from the electronic health records of patients admitted to the intensive care unit of the hospital where I work in, which is Beth Israel Deaconess Medical Center. And it has all the data that is obtained from the patients, including vital signs, laboratory test results, the waveforms captured by the bedside monitors, the notes written by the nurses, by the doctors, by the social workers, as well as images. So this latest version contains 350,000 chest x-rays that are linked with the clinical trajectory of the patient as recorded in the electronic health record. The other data set that we have built and is offering to the research community is the EICU Collaborative Research Database. This comes from more than 200 hospitals across the United States, also from patients admitted to the intensive care unit. Long believing that open access to data spurs innovation and accelerates knowledge generation, our group makes both MIMIC and EICU Collaborative Research Database publicly available at no cost to any individual who completes a standard course on human subject research training and signs a data user agreement. In doing so, these data have allowed for countless projects in academia and industry, and the availability of these two data sets have made the ICU population in the United States the most studied critically ill cohort to date. In addition, the data use agreement for both databases stipulates that the codes for projects developed be shared to the research community upon publication of the manuscripts. This repository, so there is one for MIMIC and there is one for the EICU database, has led to the rapid development of reusable codes and their respective queries, with our group maintaining the repositories and making them available to investigators around the world. The availability of the codes, as I mentioned, accelerates research and promotes reproducibility by ensuring that common concepts are implemented consistently across studies. In addition to creating and maintaining databases from electronic health records, we are equally invested in training the next generation of healthcare practitioners, computer scientists, and engineers to discover knowledge encrypted in data routinely collected in the process of care. We published the textbook Secondary Analysis of Electronic Health Records in 2016, and in the true spirit of MIT, the digital version is free of charge. Since its publication, the book has been downloaded more than 800,000 times and has been translated to Mandarin, Spanish, and Korean. But the most challenging, but definitely the most fun part of what we do is creating these communities of healthcare practitioners, computer scientists, and engineers to converge around data. Our group has hosted 37 datathons and data science workshops in 16 countries across 5 continents. And in doing so, we've jump-started numerous international collaborations. Many of the projects pitched and initiated at Datathon events are eventually published in the scientific literature. And this is why, since 2016, the databases have produced more than 1,500 publications as well as conference proceedings. These events also highlight the value of making the data sets accessible to as many investigators as possible. It ensures reproducibility, and it also promotes collaboration between different investigators. So this is laying the groundwork for different groups to start building their own data sets and sharing them. And this would be really the requirement for us to be able to perform multinational, and multi-institution analysis. The approach of getting the data into the hands of as many researchers as possible and creating a collaborative ecosystem around the data has produced all these papers out of 2 data sets, including this one that was published in Nature Medicine in 2018. In this paper, we use reinforcement learning to identify the best practice around how to treat a low blood pressure in a patient presenting with a severe infection or sepsis who is admitted to the intensive care unit. But with all the excitement and hype around data science, big data, machine learning, and artificial intelligence, we may be on track to follow the missteps of the electronic health record. Progress in machine learning has certainly outpaced the adoption in healthcare. For every tens of thousands of publications and conference proceedings on medical algorithms, only 1 or 2 are prospectively evaluated with clinical endpoints rather than model performance as outcomes. The handful of trials that have been published, and so far only 4 has been released in the medical literature, failed to demonstrate measurable improvement in population health. And with little input from providers at the front lines of care, data scientists are predicting disease trajectory and resource utilization that are clearly more heavily influenced by social determinants rather than vital sign measurements, laboratory test results, and radiologic images. The machine learning community flocks to specialties where data sets exist, and these are in critical care, radiology, ophthalmology, pathology, gastroenterology, rather than in specialties where there is a need for machine learning. And these are the specialties where there is a dearth of randomized controlled trials. I'm talking about pediatrics, obstetrics, and gynecology, surgery, and primary care, where machine learning can have the biggest impact. The problem is that no data sets really are available for these specialties. The US Food and Drug Administration has so far approved more than 40 artificial intelligence products in healthcare in the past 5 years. But most of these have very little evidence to support their use with regard to improving patient outcomes. None of the artificial intelligence products sold in the US in the domain of healthcare has been tested in randomized controlled trials. Most of the highest valued startups in artificial intelligence in healthcare have limited or non-existent participation in the scientific literature. And according to this report from last December on artificial intelligence in healthcare by the National Academy of Medicine, there's been very little research on whether the 320,000 medical apps that are now available actually improve health. And even more importantly, majority of the algorithms are being trained and validated on data from only a handful of countries, further reinforcing the tradition of a medical knowledge system that feeds into health inequities around the world. We need a better roadmap to leverage the value of machine learning and derive knowledge from the zettabytes of health data we collect in the process of care. And finally, during this time of the pandemic, an unprecedented volume of academic literature has been produced. Much of the literature has been made available to the public at record speed on preprint servers or through expedited review processes at major hospitals. But more than ever, as we have learned with high-profile retractions this past spring, medicine needs to incentivize good research practices. Standards of data sharing and standards of code sharing must evolve to publication policies and requirements to encourage third parties to reproduce studies. Last year, we published an editorial in Nature Digital Medicine where we warned readers that the excitement around big data means that we will soon be drowning in publications touting sensational findings and models with near perfect accuracy that cannot be reproduced. The research economy cannot turn all its incentives towards novelty, emphasizing sensational results to generate attention and prestige. What is important is to make sure that we have a system that takes reproducibility seriously and incorporates voices who know how well-intentioned scientists can be led astray. The health of the research environment will directly affect medicine's ability to improve the health of human beings. And with that, I'm happy to answer any questions from the audience. I think you're muted.
Yeah, it's a very nice presentation, Dr. Leo. It is very interesting to hear your thought on the how very important here the collaboration or the partnership here between the humanity includes, I think, medical practitioners, scientists, and engineers to support intelligent machine development, of course, in a medical revolution technology. So it's time for Q&A session. Okay. Please, for the participants who wants to ask the question to Dr. Leo, you can raise your hand and then you can ask your question directly to Dr. Leo. Or you can type your question on your chat box. Okay. Wants to ask. Okay. Yeah. Dr. Leo, it's a very interesting research, I think. When I read about some of your research project, one with the title Democratizing Artificial Intelligence in the Healthcare. So this is, I want to ask, how the significance of AI program here that can support to build the powerful tools for analyzing electronics medical record data for patient diagnosing and treatment. Meanwhile, I heard that some doctors here a little bit worried about the existence of AI here. They worry that AI can steal their job because everything is replaced by the machine. And then we face a barrier too when we want to make a data revolution in healthcare. As we know that the medical data is private. So what should we do here to develop the medical data research here by using AI technology? So
Let me address your second question first about data privacy. So the data sets that we have made available have been de-identified. That means that we have removed information that could re-identify someone and link it with another database. So when you access Mimic, you're not going to find any names, you're not going to find any address, you're not going to find any telephone number or zip codes. All that information has been scrubbed, and it's going to be really difficult. And we've done some certification to make sure that that you cannot look for a particular person and find them using the data set. So Mimic has been around for more than a decade, and knock on wood, there has not been any breach of patient privacy. And as you can see, the value that Mimic has contributed to not only healthcare but to the machine learning community is difficult to underestimate. So it's always weighing the risk and balance of the potential harm versus the benefits that you could have. And I think Mimic and the EICU datasets are a testament that it is possible to share data. It is possible to make the data accessible to thousands of investigators without compromising patient privacy, without compromising patients' rights. And then in terms of your question about doctors fearing that they're going to be replaced, I would say there is no reason to think that. What's more important to understand right now is there's a shortage of doctors around the world. In certain countries, you will have one doctor for every 10,000 people. And these are the situations where we really think that medical artificial intelligence could provide so much value. So the doctors who are all living in cities anyway, I don't think you're going to be replaced. What we're hoping to find to provide is that for people who live in rural parts of the country where there is no doctor, there will be a computer who can work with a human in the loop still, like a healthcare worker, to provide the same quality of care in terms of ordering tests, in terms of prescribing treatments. So those are the populations that we really want to serve using this technology. It's not going to be in the cities where you have thousands of doctors, and those doctors will continue to have jobs even in the advent of artificial intelligence. But what we would like to see is that in places where no doctors want to live, in the most rural areas, there will be some option in terms of getting good quality of care.
Yeah. Okay. Thank you, Dr. Leo. It's a very nice answer. Yeah, I think the AI here and machine learning technology actually can support the doctor to take care the patient. That we know that we as a developing countries, it is we have a limitation the number of the doctor comparison with the number of our population here. So okay, I see this is a one participant then who wants to ask to the question to Dr. Leo, Mrs. Chandrawati Putri Wulandari.
There's one before that. There's also Alfian Putra Unair who asked the question about
Yeah.
how to make sure that research is reproducible enough. And
Yeah.
to us, the biggest safeguard that we think in terms of um, prioritizing reproducibility is to make the authors share their data set, make the authors share their GitHub repository, share their Jupyter notebooks. Because if you know that someone else will try to replicate your analysis and that they will be able to do so, I think you will be less tempted to try to repeat your analysis until you get the results that you want. So to us, one of the solutions to the problem of reproducibility is to mandate the sharing of de-identified data, to mandate the sharing of codes and queries so that other groups can reproduce your analysis. And not only that, other groups can build upon your research. So now they don't have to start from scratch. They could reuse your codes and start asking new questions. So that to us is the biggest value of making these data sets publicly available. And then the second question from Ms. Chandrawati, how do you ensure that the data
pattern
electronic health record are trustworthy? So you've heard about medical artificial intelligence as being black box, and sometimes you don't know how a decision was reached. Those were in the olden times. Now you are able to interrogate black box algorithms. There are now methodologies to figure out what led to a certain decision that was delivered by a computer. So AI interpretability is one of the hottest fields in artificial intelligence, and there are different methodologies that you can use to figure out which features led to a certain decision.
Okay. Are you satisfied, Ms. Chandrawati? Yeah. Is there any question from the participants? Yeah. Okay. Thank you. Dr. Leo, I see that you use reinforcement learning model here to predict the higher survival rates for the patient. So I know that reinforcement learning is a one of machine learning type with stated by the Markov decision process. So this method is no need input-output pairs for labeling. That is just very tedious. We know that for the input-output labeling, as well as the other deep learning method. So what is the excellencies here of reinforcement learning here when comparing with another deep learning method when processing the medical data?
Yeah, I mean, so different approaches, different methodologies have different uses. So depending on what you're trying to do, deep learning might be better, for example, than reinforcement learning. So for classification or prediction tasks where you have really a large number of features, and a good example is a medical image. As you can imagine, there are millions of pixels that are all candidate variables. For those type of tasks, then deep learning would be an appropriate approach for classification or prediction. And we've seen a lot of deep learning methods such as LSTM or CNN. Those are typically used for computer vision, especially in the field of medical imaging. Reinforcement learning is particularly suited in terms of finding the best treatment policy. So the example that I gave you earlier, the paper that we published 2 years ago, is looking at how do you treat hypotension in a patient with an infection in the intensive care unit. And there are three options. One is you could ignore the hypotension. Number two is that you could give intravenous fluids to bring the blood pressure up. And number three is to start or increase the dose of a medication that artificially raises the blood pressure. I could tell you that each of those three have would have some risk if you performed it in the wrong patient. And this is a situation where there are really no guidelines. The way we make this decision is that it's highly dependent on the experience and the knowledge base of the doctor or the nurse taking care of the patient at that point. So as you can imagine, there will be so much variation in the treatment of a patient that looks similar in different institutions. And that's what you're trying to take advantage of in reinforcement learning. You're trying to model by pairing different actions with either rewards or punishment depending on the outcome. And that is the idea behind reinforcement learning. The problem with reinforcement learning in healthcare is that you don't have all the options. So you heard of AlphaGo, which is the reinforcement learning that was used to build an algorithm that defeated a human expert Go. With a board game, you could test out different moves and you will have a result for every move. In healthcare data, we cannot test out everything. There are only very limited options that doctors would find suitable for a particular patient. So in reality, it is not really the optimal action that is being determined, but it is the optimal action based on what has been experimented on by the different doctors captured in the electronic health records. So here you could see that the type of machine learning methodology that you're going to use depends on the type of question that you're trying to address.
Yeah, okay. Thank you so much, Doctor. And then there is other question from Mr. Limpat Salamat. Dear Dr. Leo Anthony, I'm interested with your statement that big data could be implemented due to the shortage of doctors' number. Is that mean that in remote area we could rely and implement big data for diagnosis instead of sending doctor? So
what we would like is, so right now, as I said, there are very few doctors in remote areas. And I think that needs to be addressed. And unless you require the doctors in the cities to start moving to rural areas, you're never gonna find a solution to that problem. So one of the compromise I think that we could do is to arm the doctors and arm the community health workers in remote areas with computers to help them in terms of making diagnosis, in terms of choosing the best recommendation with respect to treatment. So still the optimal solution is increase the number of doctors and nurses in remote areas. But we know that we've been trying to do that for the last 100 years and it's not working. So somehow we need to think outside of the box. How can we improve the situation when a lot of the doctors don't want to work in those remote areas? So perhaps connect using some of this technology to help whatever number of doctors you have now would be the next best thing. So I'm not saying again that the machines can replace the doctors. I think the best scenario would be doctors working with computers. So it's not doctors versus computers. It's doctors versus doctors with computers. And in that battle, we know who's gonna be better, because as in other parts, as in other domains in society, we are now really leveraging the powers of computers, whether that's in banking or commerce. And we know that there is value in the abilities of these computers to make the computation using so much data. Like as doctors, and I'm the first one to say that, I mean, my mind is not 100% at 2 a.m. in the morning. So I admit that I make mistakes. And I think I'm going to be less likely to make mistakes if I'm working with a computer who's really looking at all the data that pertains to a patient. So that is the scenario that we're envisioning for the future.
Yeah, okay. This is from Shiva Hasana. I think Mrs. Shiva really very impressed of you, Dr. Leo, that I truly appreciate your insight in the webinar, and hope you don't mind to share your milestone, whether it is about gain, pain, and challenges and others in learning and excelling this specialist that we so have for helpful for me to learn from your experience too. Yeah, actually, I'm attracted with your profile here that you leave your job as a doctor, right? And then you decided to take two courses respectively in the public health in the Harvard University and then medical informatics in MIT. So I don't know what is your reason here. Maybe your curiosity that we need really need a collaboration here between the medicine knowledge and then engineering and scientist knowledge here. What do you think, Dr. Leo?
Yeah, no, so I'll try to answer the question of the milestone. So as I mentioned earlier, I was born and I grew up and I went to medical school in the Philippines and then moved to the United States for residency training. The reason for that is my family migrated to the US. My mother actually was a nurse in the US. So when we were growing up, she was in the United States. That's the typical story of a Filipino family where the parents are abroad trying to earn money and send money back home. And then I was a full-time clinician, but I actually got very frustrated because what I found is that there's so much uncertainties in the practice of medicine. The way we were trained, though, we were made to think that everything is black and white, everything has the correct answer. Then when I started practicing more and more, I realized that there is no right or wrong answer. It all depends on the patient, and there's so much that we don't know. So when we have a clinical trial, for example, to determine whether certain drug is effective for a particular disease, all you get at the end of the trial is the average effect of the drug across a wide range of population. So knowing an average effect does not help me. So is my patient average so that he will benefit from this particular drug? So the way that this is set up right now is all about population health. It's not about precision medicine. So in an ideal world, what you want is a clinical trial for every type of patient. So you would want a clinical trial for patients who are aged 50 to 60 years old, who are women, and you look at the treatment effect for that population. But clearly that's not possible. It's too expensive to have a clinical trial for every subtype of patient. So what you do is you enroll patients with different characteristics and you measure an average effect. And that was frustrating to me because I need to know better. I need to know better if this patient will actually benefit from this particular drug or this intervention. And that's where I went back to school and studied about biomedical informatics, studied about data science, and studied about public health because it turns out that having the right tools is not enough. You have to have a strong healthcare system, and you need to be able to incorporate your tools into the clinical workflow. And that requires an understanding of the system itself, including the infrastructure of the people, and more importantly, as it pertains to my field, infrastructure of the data. And that's why I decided for 3 years to stop practicing medicine, go back to school, be a student full time, and then go back to practice now armed with a special skill set to hopefully try to address the problems that made me go back to school in the first place.
Very inspirative story, I think, Dr. Leo. So this is the question from Professor Suryanidia Astuti. I would like to ask you, what do you think about the use of AI on electronic nose for COVID detection, which is currently being developed? How accurate is it? So do you know electrical nose here? Maybe you ever read about this research?
So, I mean, I don't know specifically about this, but I would presume that this will be trying to detect COVID from certain features, right? And those features may be based on some wireless sensors. So the most important thing is that um, the that before you deploy any AI, that you evaluate it on the population that you would like to use the AI for. So you do not buy AI from the United States and deploy it in Indonesia, because I could assure you that that AI will not work. What you need is AI that is developed using Indonesian data. That is the most important part. And that's why I'm very much against buying and selling of AI algorithms, because I think that that is the wrong approach to AI. The people who are doing that don't understand AI, because AI should be dynamically recalibrated. It might perform well now, but a year from now, it's not going to be as good because there has been a change in the behavior of the people. There has been a change in new tests and treatments that were introduced into practice. So to me, what I would like you to take away is that if Indonesia wants to be a leader in the field of medical AI, you have to invest in developing and curating the data sets coming from Indonesian patients. You have to make these data sets available to computer scientists and engineers rather than just one or two, because what's going to happen is they're going to develop models that no one can reproduce. So making this data set available to a large group of people, I think, is a safeguard that what they're going to be producing are models that can be replicated if someone else would try to repeat the modeling that was performed. So data is important, but at the same time, data is also like crude oil. So most of the time, the data that you have now is not ready for machine learning. So the data has to be integrated from different systems, and you also harmonize concepts. You have to make sure that if you're looking for a blood pressure, it is represented similarly across different data sets. And that's no guarantee. And this is why a big chunk of our time and effort is invested into what we call data curation. cleaning the data, pre-processing the data. It's very difficult. The machine learning is easy once you have a data that's curated already. High school students can build the most elegant deep learning models if you give them the right data set, it is you give them the right question. The hardest part is putting together the data set and having the clinicians curate the data set. No nurse or doctor would like to curate. They don't want to go through 3,000 entries of insulin and tell you which ones are intermediate acting or short acting. That is the more challenging part. And this is why crowdsourcing the task to us is the best strategy. And that is the reason why we made our data sets publicly available.
Okay, thank you very much. This is the question from Mrs. Ira Puspitasari. She is our colleague from YouTube chat. Is it possible to combine convolutional neural network and recurrent neural network for medical image processing, for example, for diagnostic tool? Have physicians and medical doctors evaluated these AI-based diagnostic tools?
I mean, I would suggest to evaluate them separately. The good thing is that with machine learning, you can always tell whether your approach is correct if your model is performing well on a test data. My favorite answer when my students would ask, should I do this? Should I do that? My answer is always, why don't you do both and see which ones would give you a better model? So sensitivity analysis is always the standard answer for machine learning. So if you would like to combine them and see if they perform better with the combination. So what we're trying to do now is combining reinforcement learning with causal inference methodologies such as targeted maximal likelihood estimations to see if we're able to get better estimates of our treatment effects. So we're going to find out whether that approach is better or not.
Okay. The last question, Dr. Leo, from Mrs. Fadila Colby. So as we all know, data science has been playing a significant role in economic and business purposes. My question is, how far is the data science have been implemented in medical practice today?
Not very far. Not very far at all.
Not very far, still not very far.
No. And the reason is that the data is still very, I think, very nascent. So especially in a lot of countries. So most of the data sets are coming from radiology, ophthalmology. They're coming from the United States, the UK. And as I mentioned earlier, you cannot use these models in other countries because those models would fail because the relationship of the features with whatever you're trying to classify or predict will be different if you go to Uganda or you go to the Philippines or you go to Brazil. What is important is really using local data to build local algorithms. And we need more help in terms of building these data sets. That's where we need investments on. And that's the reason why we haven't gone very far when it comes to artificial intelligence in healthcare compared to artificial intelligence in language translation or retail or marketing. So without the data sets, we cannot progress. So we need those data sets, and we need communities around the data sets to help each other and take advantage of each other's expertise.
Yeah, okay. I think the time is up for the participant here for the question and answer session. Okay, I got the point here from our topic discussion today that the data is very significant here, Dr. Leo, I think, for the AI methodology, AI performance here to development of such some of a medical technology. So the research collaboration here is very important in medical technology development, we need to integrate our work with medical professionals, scientists, and engineers to create innovative medical technology. So it can find across the whole care pathway, and we can accelerate the recovery for the patient and keeps the people, of course, being healthy. So, okay, for all of participants, we hope this webinar will be beneficial for us. I would like to say many thanks to Dr. Leo for his valuable sharing. Thank you very much, Dr. Leo, for your time. Thank you. And thank you all for your attention. Okay, let's give a big round of applause to Dr. Leo for his very nice presentation today. Thank you very much, Dr. Leo. So I offer the time to Miss Osma here. Okay, please, Miss Osma.
Yeah, thank you, Dr. Idris. It was such amazing session with such amazing speaker. And thank you for sharing such interesting knowledge with all of us. For the next, I would like to invite all of the participants to open the camera and we will take a picture together. Please open the camera and we will take a picture together. I think Dr. Leo has already left the meeting. Sorry.
Okay. Yeah, because he has an important meeting, I think. Actually, okay, Miss Osma, you can continue our second session, I think.
Yes. Okay, thank you, ladies and gentlemen. Now, I would like to introduce our second moderator, Mr. Alfian Pramudita Putra, STMSG. Mr. Alfian is a lecturer in Biomedical Engineering Program, Department of Physics, Faculty of Science and Technology. Please give a warm welcome to Mr. Alfian Pramudita, STMSG.
Thank you, Ms. Osman, for the time. And here I will be the moderator for the second session. So our speaker for the second session is Mr. Cho Wei Lin, PhD from National Cheng Kung University from Taiwan. My name is Alfian Pramudita Putra. I am a lecturer from Biomedical Engineering Study Program, Department of Physics, Faculty of Science and Technology, Universitas Airlangga, Surabaya. I will read the short CV of Mr. Cho Wei Lin from NTKU Taiwan. He finished his PhD from Department of Electrical Engineering, National Cheng Kung University, Taiwan in 2011. And his research interests are biosignal analysis based on artificial intelligence algorithm, development of smartphone healthcare applications, medical application of virtual reality system, and medical wearable device design. And I would like to say hello to Mr. Cho Wei Lin.
Hello, can you hear me, guys?
Yes, it's clear in here. How are you?
Very good, and it's very happy to join with you in the World Congress University program of the Big Data and Artificial Intelligence in the Future of Medical Technology. It's my pleasure to be with you here. And I'm so happy to join you because I visited Indonesia three years before for student recruitment, and I visited several cities in Indonesia, and I love this country. And now in my lab, including the Miss Nurul Diana, May Diana Nurul, there are 4 students, graduate students from Indonesia in my lab, research lab. So I really love to cooperate and also contact to Indonesian guys. So it's my pleasure to share with you of my research here. So now I'm going to share my slide, but please allow me to check how should I share my slide here. Please give me 1 minute to do it. Okay.
Okay. Thank you for joining us in this webinar. Maybe I will read the topic that you will give to us today. The title is AsiaSafe, AI-based screening equipment of arrhythmia and structural heart disease using artery fibrillation energy. And I hope it will be very nice presentation. And for the participant, if you have some question, please write down the question in the Zoom chat column. And also, if some of the participants from the YouTube channel, please also write the question in the YouTube chat, and then some of the committee will forward the question to the.
I cannot share my slide.
Oh.
Yeah. Sorry, I cannot share my slide right now. So, share screen. I don't have that one. How to share the screen?
Yeah.
Do you already open your presentation?
I already opened my presentation, but unfortunately, I got some technical problem in my pad, so I cannot share my slide here. I don't know why. So maybe at this time point very fast, I think I will change my slide to my computer. So that might be better. I can use this one.
Okay, no problem, yeah. Mr. Lin. You can take your time. We will wait for the presentation.
Sure, no problem. And during this time, I think I can introduce a little bit about the things I'm going to share in today's presentation. Okay, because in today's presentation, I'm going to share our experiments in using the. Okay, so sorry, I can change my video right now. So I'm going to quit in my pad. Wait me for a while.
Okay, no problem. Okay, we still need to wait for the Mr. Lin to join us again because there is some technical problem. So I will read again. The topic is the title is AsiaSafe, AI-based screening equipment of arrhythmia and structural heart disease using artery fibrillation energy. So it's kind of like the application of the artificial intelligence in screening equipment or diagnostic tool for arrhythmia. So it's some kind of disease in the heart. And for the kind of like a medical signal that the Mr. Lin used is artery fibrillation energy.
Why his voice is so little? Oh.
Are you with us, Mr. Lin? Okay, we still need to wait for Mr. Lin to join with us again. So after the presentation from Mr. Leo about the big data in medical application, so for this one, Mr. Lin will talk about the application of the artificial intelligence itself, especially in the cardiology field. Again, I would like to remind for all the participants, if you please rename your Zoom name into the name _ the affiliation. And also, if you have some question, you can send them in the Zoom chat, or also by our YouTube channel. You can also send the question in there. Hello, Mr. Lin, can you hear us?
Yeah. No?
Yes, Professor Lin. I think we can hear you. Is the presentation on already open?
Hello, everyone. Can you hear me right now?
Yes, it's clear from here, Professor Lin.
Okay, you can hear from me right now.
Yes, but
okay, thank you very much. So I apologize for my delay. So now I'm going to start my presentation right now. Okay.
Yes, please.
Okay. Thank you very much. And okay, at the beginning, I apologize for the technical problem. And right now, I'm going to present our study as the AI-based. Can you see my screen right now?
I think it's not yet. It's a white blank screen.
Say that I'm sharing right now.
Maybe you share the wrong window or something like that. Maybe. If the presentation is in the Microsoft PowerPoint, so you can share the PowerPoint window. Oh yeah, this one.
Okay.
Yes.
Okay, so good morning, everyone. So today I'm going to introduce my topic, which title as the AI-based screening equipment arrhythmia for structural heart disease using auditory vibration signal, and we call this project as the AC Safe for our project. So at the introduction part, I will state a little bit about the disease fundamental, prevalence, and the unmet need of our project. So far, you know that around the world, according to the statistics from WHO, there is 17.7 million deaths in 2015 were attributed to cardiovascular diseases. So that we know that cardiovascular diseases is the #1 cause of the deaths globally. And we can also know that nearly 3 in 1 death is related to cardiovascular diseases. So how to efficiently screening out the cardiovascular disease is our critical unmet need. And we also know that the prevalence of cardiovascular diseases is very much around the world. So our unmet needs and our expected solution is to utilize ARM, which is one kind of embedded system, and a deep learning algorithm in the application of the screening device of arrhythmia and the structural heart disease screening. So that is our goal of our project. Okay, so you can see that in the traditional, the cardiovascular diseases can be categorized into 3 different categories. They are 3 main categories, including coronary heart diseases, arrhythmia, and the structural heart disease. And in our study of here, we focus on the development of the arrhythmia and the structural heart disease screening. Okay, so at the beginning of our presentation, I would like to introduce that traditionally, in the medical standard of diagnosis of the arrhythmia can be utilized by electrocardiogram or medical images such as CT or MRI or even the blood test. However, those measurement technology always can be used in the big or medium hospital. It is not very wide spread in the rural area or the small hospital or even the clinics. So we would like to develop a portable device and the embedded system that can utilize in everywhere, and but with very smart and intelligent diagnosis and the screen capability for users to do it. Okay, the concept of our project actually is come from the Professor Liang Mingcai, who is a very senior cardiovascular disease physician in Taiwan, and he was the a retired professor of our university hospital. So because he is a very senior professor and cardiovascular disease clinical physicians, so he told us that in his when he was young, there is not so many equipment related to the just like the electrocardiogram or other devices. So they need to utilize their physical examination to feel the pulse from the radial artery. The radial artery is the artery on your wrist, just like my mouse pointed right now. So so we can know that if we can based on his experiments, if we can based on his experiments, then we can do a very smart device for collecting the data and also use the data to examine the certain kinds of diseases. Okay, so what we have done in here, including the abnormal discharging and organic damage. In the abnormal discharging, we have the data from atrial fibrillation, atrial flutter, VPC, and APC. And in the organic damage, we have the data from aortic regurgitation, aortic stenosis, and the congestive heart failure, and the hypertrophic cardiomyopathy, HCM. So in our university hospital, we collected the data from those one and to do our clinical trial. So basically, in this slide, I would like to let everybody know that in the when our heart contracts the our blood into anywhere inside our body, we have lots of physical signals can be utilized to describe the activity of our heart contraction. For example, from the chart in my left-hand side, we can see that we can have the data from the electrical activity, just like the electrocardiogram, and also the blood pressure variation from the our blood flow, or also the sound, just like the phonocardiogram in our heart. So we can have lots of different signals can be utilized to diagnose of our heart activity situation. Because what Professor Tsai or Dr. Tsai has in his experiments is to collect the waveform in the radial artery. So at the beginning of our study, we attempt to utilize some sensors to collect the data from radial artery. And I also attended the large part of the Professor Dr. Anthony's presentation in the previous seminar. And one opinion and the one point of view from the Professor Anthony impressed me a lot is that Professor Anthony said that how to get and make sure the correctness and the cleanness of the original data in your machine learning or deep learning application are very essential. So because the data we used actually is not come from the standard medical procedure, because in the standard medical procedure, the radial artery waveform may not be collected. So we need to build our own sensors to collect the data. So we spent almost 1 to 1.5 years in collecting the data from our radial artery, and these are our prototype of the our radial artery waveform sensor. So based on this slide, you can see that we place our sensor actually is composed of the microphone on the top of our radial artery. Then we collect the data, the waveform like this. So you can see the peak of the waveform here indicates the peak of the blood flow, which eject to our radial artery when our heart contracts. So from this waveform, we can know that we successfully develop a system that can collect the data and the vibration from our wrist artery with respect to the different shape of the radio artery. Okay, then in here, I would like to show you a little bit demo of the real data collection of our system. So at the beginning, the users may touch the radio artery by hand sensing. Then we can use our system to collect the data from our radio artery, just like this. So at this timing point, we are happy that we successfully collected data from our radio artery, but our problem is that how to continuous collect the data, and but also to analyze the difference from the data in different kinds of the heart diseases. So we do some modification in our on our sensors, and this is another type of our prototype. So you can see that it used a clip to mount the sensor to collect the data. So we have more long time to collect the data here. However, after we collect the data, actually we collect the data from the patients in our university hospital. And here I shows two examples. One example is from the sinus reason from the normal and healthy subject. So in the upper part of the waveform, it is the sinus reason of the subject, and you can see that we collect his waveform, and we name our waveform as the PAG, which means the pulse audiogram. So I will use the terminology PAG to indicate this is our waveform in the later part of my presentation. So in the upper part of the figure, you can see this is the time domain signal of the sinus reason PAG, and in the lower part of the figure, this is the PAG of the atrial fibrillation. So our problem is that can PAG discriminate difference between sinus reason and the atrial fibrillation, this well now and the high prevalence arrhythmia. So we would like to see if there's any kinds of methodology can help us to do the successful classification between different kinds of the PAG. So I would like to jump to another concept a little bit while, because the topic and the main thing of the web seminar today is the big data and artificial intelligence. So I would like to say that the artificial intelligence changed the trend of our research development a lot. I think everyone know that the Alan Turing is the, maybe we should say the founder or the first researcher who is doing the artificial intelligence related subject. So so during our research period around 2017, you know that during that time the AI started to booming around the world. So one day my colleagues asked me, Professor Lin, recently the AI is very hot, and do you have any project that is appropriate or suitable to present it or to use the AI to solve the problem? So at that timing point, I have a feeling that maybe I should think a way to transform our time domain signal into the image-like features in order to combine the sophisticated deep learning models such as the convolutional neural network in our system. So at that time, we use the so-called time frequency transformation approaches in our study. So in our study, at the first time, we would like to transform our data like this into an image-like feature. So this is the original raw data of our system, and so we use the so-called time frequency transformation, and or you can say continuous wavelet transform. We transform our data into the figures here. The horizontal axis of this figure is time, and so as the second figure. And the vertical axis in this figure is the amplitude of the signal, and the vertical axis of here is the frequency range of the signal. And then the figure color of the figure is the density of the signal in each different frequency band. So based on the observation from the upper figure and the lower figure, you can find that there is a significant differences between the waveform which collected from the sinus recent and the atrial fibrillation. So we think to transform our data into spectrogram is feasible to discriminate the different kinds of heart diseases. So next, we extend our research to different kinds of heart diseases. For example, this is the spectrogram from the sinus recent, and this is the spectrogram from the atrial fibrillation, and the spectrogram from the atrial flutter, VPC, AS, AR, congestive heart failure, and the HCM. So we found that in the different kinds of the heart disease, we can find different patterns from the PAG spectrogram of each heart disease. So this makes us happy and confident. Then we can use the convolutional neural network or other similar deep learning related works in solving the problem here. So we start to use the AI to solve our problem, and the main thing, the main classifier we use is so-called convolutional neural network. Okay, so after that, you can see that we use the AlexNet convolutional neural network to solve our problem. Then here, I may introduce a little bit demo to our system to you. So after that, we implement our system in an embedded system. So at the beginning, the users will mount our sensor on their wrist. Then we will start to collect the data. And after we collect the data, then we can collect the graphic. We can plot the graphic of everyone's data on their wrist artery. Then after we press the classify function, because we already implement our deep learning classifier in the embedded system. So we have a portable system that can directly measure our data and plot the data, and also classify the data directly on board. So this is almost the, we almost finished our proof of system, and now we are doing the large scale clinical trial in our university hospital to prove that our system can measure up to 15 different types of heart disease by only using the radial artery PAG waveform. Okay. So according to the accuracy, I would like to introduce the accuracy of our system in several different ways. Okay. The first one is that because we not only implement our system and the program in personal computer, we also implement our system in embedded system, which is named as the ARM embedded system. So you can see that when we implement our system in MATLAB of our personal computer, then we can get the spectrogram in image size of 227 by 237 by 3. And when we implement our algorithm in ARM embedded system, so we will have less or smaller scale of the image. And in the computer, we spend 1.5 seconds of the computation time, and in the STM32 of ARM, we spend 7 seconds, and for the precision, it's almost the same. Okay, And in order to verify our algorithm is correct in the embedded system, so we first download the data from, we download the electrocardiogram from data, although we are not using the electrocardiogram in our project, but we utilize the electrocardiogram data from the internet to check the availability of our hello. So you can you still hear me? Okay.
Yes,
okay. Now because Miss Diana is sitting next to me, and she told me that the video got stopped for a little bit. So I would like to repeat a little bit in this page because in order to verify the system and the algorithm we implement in the embedded system is correct, so we also download the data from the internet, which is the MIT atrial fibrillation database, and we verify our algorithm in ARM embedded system. Our own embedded system is named as the STM32F7. So you can see that in our PC program, we utilize the MATLAB and the Python to implement the AlexNet and our so-called simplified CNN, and also we use the simplified CNN in embedded system, and we use the fork cross validation in the MATLAB of the program personal computer, and we use the 70% of training and the 30% of testing in Python and STM32. And finally, we got a very similar accuracy, which is the 93.87% of the accuracy when discriminating the atrial fibrillation data and the sinus reason data in program on personal computer and the program in ARM embedded system. And if we use our data, which we collected from our NCKU hospital, and we collect the data of the sinus reason for 336 samples, and we collect the atrial fibrillation, one of the arrhythmia, up to 417 17 samples. Then the accuracy is we got in our system is 100%. So our system can almost successfully classify all of the atrial fibrillation data to sinus reason. That is a normal habit. And after that, we do our classification in multi-class classification. We put the sinus reason, atrial fibrillation, and also the atrial flutter, APC, and the VPC. We collected 5 different kinds of data together, and then we would like to do the multi-class classification. And you can see that finally we got the accuracy of 87.24% in our study. And in the next, we would like to do the multi-class classification in the structural heart disease group. So we we collect the data from the sinus reason, aortic regurgitation, aortic stenosis, congestive heart failure, and the HCN together. Then finally, we got the accuracy of the 97.1% in our data collection. So we will know that our system is capable to screening out the system of everyone's heart disease. So at the last, we implement an AI-based screening equipment, arrhythmia and the structural heart disease device, and we effectively do the early detection of arrhythmia and the structural heart disease, and we only need to use 8 seconds to get the classification result. And our system is very low power consumption. We can only utilize 3.97 watts on our appliance. So this is the last page of my presentation. But however, this is not the last of my presentation because I still prepare a video and wants to share with you. So right now, can everyone see my presentation, my slide in the YouTube? Okay, so I think everyone can see that, and I'm going to play our video to you. Can you hear the voice from YouTube? Okay, so I will use the YouTube to our video to quickly let everyone can know our presentation in the system again.
Can you increase the voice of the YouTube, Professor Lin?
The voice?
Yes.
Can you hear right now?
It's still not fit yet.
Can you hear the voice right now?
Not yet. So maybe you can go to the view option of the Zoom, and then there is.
I think I can. I think I can hear my voice. Okay, I think because Diana told me that everyone cannot hear the voice from the video, so I will introduce you the voice from my presentation. So just like my presentation at the beginning, we think the cardiovascular disease is a very important issue that need to be solved. So because that the atrial fibrillation is one kind of the very high prevalence arrhythmia, and it can easily to lead the stroke. And however, for some novel medicine technology, if the people who has the atrial fibrillation can early take some kinds of the pills, then the prevalence of they suffer from the stroke will highly decrease. And so we would like to solve, we would like to screening out the patient with the atrial fibrillation by using our system. So we propose our system, which title as the AC Safe. And based on this system, we integrate the ARM embedded system platform with AI-based screening system and the electrocardiogram and our wrist artery vibration signal. And our algorithm and our methodology also obtain a Taiwan government's patent. So we introduce our system. We name our system as the AC Safe, just like the name you can see here. And the characteristics of our system is that this system is easy to use. Then we can know that it's only single lead electrocardiogram, and with the wrist artery, we can have the wrist artery vibration here. And we also have the edge computing in ARM embedded system. And in our ARM embedded system, we implemented the time frequency transformation and the deep learning neural network. And in our university hospital, we collected data from the subject, each of them with 10 minutes long signal. And finally, we transform our algorithm, which developed in the computer, into the embedded system like this. So it's we already implement the system in our embedded system, and then now it is ready to do the large scale experiment around the world. So if any professors or the doctors in Indonesia has the interest, we would like to invite you to join our international collaboration in adapting our solution in your area to do your research or to do the screening, fast screening of the heart disease. So this is the system introduction of our system. We use two STM32F7 discovery evaluation board. We have a user interface and the ARM embedded system, and also 1 byte of ROM and the 340 kbytes of the RAM. So our system is not very expensive, by only using I think around $200 USD. then our this is the cost of our system. So only 200 USD is needed in the adapting our solution. Of course, if you want to cooperate with me, we will not charge you any cost from this. And in our system, we have two parts. The first part is the sensing parts. The sensing parts include one electrocardiogram and one wrist artery signal collection. And we use the piezoelectric sensor in collecting our wrist artery data. And this is the collaboration with our lab and our Japanese collaborator. So, sorry. Okay, sorry. And our system also proved by the IEC 6061 medical safety approval, and this is the circuit board of our system and the appearance of our system, and this is our user interface flow. So we first we will come from the welcome homepage. Then after we press the major button, then we will start to collect the data from our system, and then next we will we can use the classifier function, which we implement our deep learning algorithm and the high frequency transformation algorithm in our embedded system, and finally the system will show our classification results. Okay, and here is the brief flow chart of the algorithm. So first, you can see that our system will collect the data, and by fixed interval sensing, or we can say analog to digital conversion. And after collect the data, then we will use the continuous wavelet transform, which is very actually we spend lots of time in implementing the continuous wavelet transform into our system. And then next we will use the convolutional neural network, and we simplify the convolutional neural network from the AlexNet. So to do this, and here are some example, and you already see it in my presentation slide before. So in this slide, you can see some difference between the atrial fibrillation spectrogram compared to the sinus rhythm, which is the normal one. And from this figure, I think this is very appropriate to use the deep learning to classify the different pattern from different disease and the different pattern from different subject. This is because that although different disease has the similar pattern, but however it still has some variation between system to system. So we would like to say that if we can use the deep learning, and the deep learning is very robust to classify the image data, and also can accept large variation. So we can see that it is capable and can doing good job in the data communication. And okay, next is our system performance evaluation. We evaluate our system performance in several ways. Okay, the first one is we try to measure if the data transmission, data transmission between the system is correct. So we use this kind of system. We use the logic analyzer to do the data communication verification. Okay, so I think the rest of the video is very similar to the result I presented here. So I will just stop my presentation here, and I would like to get some feedback or some question or some comment from every one of you here. Okay, thank you very much.
Okay, thank you very much, Professor Lid, for the presentation. It's really nice and also interesting. We also have some questions here from the first one from Miss Osmalina Rahma. Dear Dr. Lin, how the vibration energy could do the screening for the arrhythmia? Is it recording the sound of the heart rate? And why do you prefer the vibration energy rather than the other sensors, such as maybe like electrodermal activity or another sensor? Thank you.
Okay, thank you. This is, this is a very good question because if we can use if we use other similar sensor, I think based on the research point of view, we will have no novelty compared to existing literature. So to use the new kinds of signal which can bring the novelty to our system, I think we can also to develop some new observation. For example, in our study, we found that to use our system can great observe the structural heart disease, but for the traditional electrocardiogram, it cannot get the classification from structural heart disease very well. So we would like to say that by using the system of our pulse audiogram, we can better understand the hemodynamics, which means the dynamics of the blood fluid inside our body, and make the screening more efficient. Not only can screening the arrhythmia, but also can recording the blood flow and the hemodynamics of our cardiovascular system, which can make our system better in discriminating the structural heart disease and not only the electrocardiogram. Yes, thank you.
Yeah. So it's like it doesn't only differentiate between like normal and not normal one, but it can also differentiate with another several diseases. Like in this case, you also use arrhythmia and also CHD, I think. Is that correct, Prof. Lin?
Yes. Would you? Sorry. Because the internet connection is not good at that time. So, sorry. May I ask you to repeat the question again?
Okay.
Sorry.
I mean, like what you said. So it's not only differentiate between normal and not normal one, but it can also differentiate several diseases, several heart diseases.
Yes.
So yeah. Okay, so it can be more specific. So,
okay. Thank you. So I think yes, our system can not only discriminate the normal and abnormal heart disease, we can also discriminate the what kind of the specific heart disease that the subject has. So this is one characteristics of our system. So we believe that by using our system, so the doctors or the clinical physician can only use the system to the rural area or the home care medicine for them to screening and to know the disease progress of the subject in their house or in the rural area, and let the patients not necessary to the big or medium scale hospital always. So it can save patients time and can let the family medicine doctor or the doctors in clinics can have better capability to screening out the severe heart disease in their patient treatment and the diagnosis.
Yeah. We also have the second question from Mr. Akif. Dear Professor Lin, can you inform us about the embedded system and programming tools that you use in the device?
Okay, thank you. The embedded system we use here is the STM32, which is an ARM-based system. And in this ARM-based system, we use the Python and the Xcode system to develop our algorithm. I would like to share a little bit our research development progress here because we know that to implement the deep learning or the time frequency transformation, such a very complicated algorithm is not so easy in embedded system. So actually, we develop our algorithm in personal computer first. Then we use the Python to variate our we first develop our algorithm in MATLAB system. Then after we confirm the architecture and the methodology flow of our system, then we use the Python to duplicate our system and the algorithm again. Then next, we implement the code we successfully implement in Python to ARM embedded system. So if anyone would like to develop the deep learning in embedded system in the future, I would like to suggest maybe you can try to make sure and confirm your algorithm flow in personal computer with flexible software such as the Python or the MATLAB first, then implement it into the embedded system in the next step in order to save time of your study. Yeah, thank you very much.
Okay. We also have a related question with that one from Mr. Firman Ismasardana and Mr. Triwianto. The question is about the training stage of the implementation of the artificial intelligence. Did you train the CNN inside the microcontroller or use a computer to train the CNN? It's like directly in the embedded system or in the computer first?
Thanks for this question. Actually, we train our system in personal computer first because I think to make sure an algorithm can work with high accuracy to the problem we are going to solve is very important. So that if we cannot make sure the algorithm can perform well in our system, then if we train it in the embedded system at the beginning, then we just waste of our time because we cannot make sure how the result is. So actually, we train our system in the personal computer first, in the PC first. Then after, of course, we train our system in different kinds of conditions and the requirement. Then after we finalize and we confirm all the settings and all the algorithm, then we transform it into the embedded system for another trial and the training. So basically, we have two steps in our training. The first step, when we want to try the different efficiency of different network, we use the personal computer to do it. After we find the algorithm with the higher risk accuracy, with the acceptable computation time, then we try to transform it into embedded system and train again to make sure the result is identical or similar between the result in personal computer and the result in the embedded system. Yeah.
So you still need like kind of like validation, like from when you already train the data in the personal computer, and then you also train again in the embedded system to make sure that the result is the same.
Yes.
Okay. There is also a question from Mr. Gunadi. Professor Lin, in academics, it's inevitable that we need to prepare our students to be more familiar or comfortable with artificial intelligence. We don't have the computer science department in Mr. Gunadi affiliation. or expert to help the student or faculty. So knowing the limitation or using the AI will be a big hurdle. Do you agree that now it is mandatory for the students from all disciplines to familiar with programming microcomputer or microcontroller, MATLAB and Python? Maybe please also list another skill that you think will be mandatory to prepare to use artificial intelligence for the students. Thank you.
Okay, thank you very much for the question from Gunadi, right? Gunadi.
Yes, that's one.
Okay. I think, in my opinion, I think there are 3 steps of familiar with the deep learning or the machine learning. The first one is that I think and I believe that the student want to involve this should have some basic knowledge of the linear algebra, which is one kind of the engineering mathematics. Because in the deep learning, we utilize lots of the linear algebra concept in this, and of course, to knowing a little bit about the calculus, especially the derivative, is necessary. So I believe that only the student, especially the student who is coming from the engineering background, you should know the math inside the deep learning. Otherwise, when the result is not good, you will have no idea which point should be we emphasize to solve the problem. So in addition, in front of the programming, I think the linear algebra and the calculus should be the pre-required course for the student who want to participate in deep learning. And the second, in the deep learning, there are so many free and open source right now, such as the Python and the TensorFlow, or all kinds of the Keras and so on, all kinds of the available tool on the internet. So I think to join it from the Python might be the best solution if if the budget is limited. So to start from Python, the TensorFlow might be needed. Of course, if a student want to join on this, I think they should have the basic skill of the programming. So maybe to have some background of the basic programming of the Python or even the C or C++ is necessary. So I think it will not so necessary to learn too many different types of the machine learning language. You can only to learn 1 or 2. But I think more important is that maybe your student or the one who is interested in this should first try some example from internet, then use the concept you learn from internet to solve your own problem or the problem that happens around your country or your university. That you can, when you learn and try to solve your own problem, then you will have more feeling and more knowledge to using the deep learning knowledge. Thank you.
Yeah, I also agree with you that the student need to know like more the basics, so they don't only use the programming, but they can understand what is inside the program itself.
Yes, very important.
There is another question from Miss Adiratna Ciptaningrum from 10 November Institute of Technology, Surabaya. Dear Professor Lin, I am interested with your statement that deep learning can classify the data. I see the model of deep learning layer in your slide. Is there any significant output difference in the pooling layer of each model and programming tools? Thank you.
Thank you for this good question. I think I visited ITS before. Yeah, I visited ITS before in Surabaya, and this is a very big and good university. I appreciate for your question because the time limit, so I didn't introduce the details of the pooling layer and the output and even the features extracted by convolutional neural network too much in today's presentation. So if you don't mind, I will leave my email in the chatting room later. Then because that is more detailed. So if you want to knowing more about this, please feel free to email to me, and I will email you some explanation slide or the paper we wrote before for your reference in order to save everybody's time. Thank you.
Okay, so for further information and also discussion, you can contact Professor Lin directly to the email in the Zoom chat room. And also, I would like to say thank you for Prof. Lin for joining us in today's webinar. I hope everyone can gather more of knowledge and also information from Professor Lin research. And the conclusion of this session, the Professor Lin now focus on the AI-based screening of screening equipment of arrhythmia and structural heart disease, and also it's effective for early detection of this disease with high accuracy. And now this is the end of this session. Thank you very much for all the participants, and also especially for Professor Lin for joining us today.
Thank you very much. Thank you.
You're welcome.
Okay, see you.
See you. Yeah,
see you. Bye-bye.
Bye. Okay, I will give back to Miss Osmalina.
Okay, thank you, Pak Alfian and Dr. Chewelyn for sharing such interesting knowledge with all of us. And maybe without further ado, I would like to introduce our last moderator, Mr. Akif Rahmatillah, STMT. Mr. Akif is a lecturer in Biomedical Engineering Program, Department of Physics, Faculty of Science and Technology, Universitas Airlangga. Please join me in giving a warm welcome to Mr. Akif Rahmatillah.
Okay, thank you very much to Ms. Osmalina Nurrahma, to all participants. Assalamualaikum warahmatullahi wabarakatuh. Welcome to the third session of our webinar today. And in this session, we are going to discuss about the brain technology. It's really interesting topics right now. Focus on EEG signals and its application. And this presentation will be presented by Dr. Rifai Chai, a senior lecturer with Faculty of Science, Engineering and Technology, Swinburne University of Technology in Melbourne, Australia. Before we start the presentation, Dr. Rifai begin the presentation, I would like to give you information, the short curriculum vitae of him. He received the Bachelor of Engineering degree from Krida Wacana Christian University, Jakarta, Indonesia in 2000, and the PhD degree in Biomedical Engineering from University of Technology, Sydney, in Sydney, Australia in 2014. From 2000 to 2011, he has worked as electronic product development engineer with many companies in Indonesia and Australia. His research interests are brain-computer interface, rehabilitation, medical technologies, and artificial intelligence. Currently, he is a senior member of IEEE and serves as associate editor of Electronics Ladder. We greet first Dr. Rifai. Good afternoon, Dr. Rifai.
Good afternoon. Good morning, Akif.
Okay. Yes, I think it's 2 p.m. in Melbourne, right? So
yes, that's correct, yep.
I greet with a good afternoon. Okay, without further ado to Dr. Rifai, please give your presentation and the time is yours.
Thank you, Akif. Thank you as well for the introduction. Let me share my screen. Can everybody see on the screen?
Yes, yes,
that's good.
We can see it.
Thank you. Good morning to everyone in Indonesia, and good day to others outside of Indonesia. As you see, my name is Rifai Chai. As you away from Pak Akif introduction, I'm actually from Indonesia as well. So it's my home country. I'm from West Borneo or West Kalimantan. Okay. And first of all, I would like to thank you as well to the committee. So you can see from the Department of the Physics and Faculty of Science and Technology, Universitas Airlangga, for the invitations. It's my honor and pleasure to be here to present my research to everyone here. And the second thing is I would like to thank you to everybody for participating. I can see there's quite a large number of people here. Thank you for attending this presentation as well. And this presentation is part of the world-class university programs with the team Big Data, Artificial Intelligence in the Future of the MedTech, Medical Technology. So you can see the keyword here is Big Data, AI, and the MedTech is very much aligned with my research. So my field of the research is biomedical engineering and AI as well. You can see today I will present about my research in brain technology, a particular technology and its applications. And let's have a look to go further. Let's review back on what's technology available for the brain. You can see in terms of the technology, we can see from the invasive or non-invasive. For the invasive, mainly we can check from the electrical signal. So we need to put the sensor inside the brain to measure from the cortex of the brain. You can see there's few sensor here. It can be a microelectrode. Microelectrode is just have to be touched to the cortex area. And the other one called ECOG is the electrocardiography. Is a semi-invasive but need to do operation. It's like between the cortex and outside. It's like called in a dura matter. So that's same thing as well. They measure the electrical signal. And the other part of the technology can be non-invasive. So the popular one is measured by the electrical signal from the scalp of the brains. We use that EEG or electroencephalography. It's very popular in hospitals. Hospitals use that a lot for measuring the brain signal. Some of them use for clinical study on epilepsy, sleep study, for example. Also, you can use magnetic sensor, what they call MEG, so magnetoencephalography. And the rest is based on the imaging technique. So for example, you can use FNIRS, functional near infrared, so near infrared spectroscopy, or fMRI, so functional MRI machine, something like that. Or PET, this is a positron emission tomography. So you can see these three of them is imaging techniques. They measure the blood flow or blood oxygenation. And it turned out you can see in terms of the publications from 1990 to 2019, the EEG become large attention on that one. And that's the reason my research pay attention on EEG as well. And another thing is EEG, we can make it modular. So it's temporal demise is quite fast. Although some disadvantage, for example, they have easy with the artifact, tend to get artifact there on the EEG and other kind of disadvantage. But the concentration of the research at the moment I'm doing is using the EEG. Okay, so that's same with the title that I provided. So EEG is the chosen technology, the brain technology that I'm doing at the moment. Okay, now to do this one, we need an AI, so artificial intelligence. By definition of AI, is artificial intelligence is the intelligence that demonstrated by the machines. In order to do that, we need the data. That's why you can see to start to the system, we need to collect the data, signal measurement there, and from there we do have do with the signal processing, so including signal pre-processing. We need to clean the noise, we need to clean artifact from the EEG. And from there, because EEG is a very noisy signal and is what we call a non-linear and non-stationary, we need to come up with the features extraction as well in there. And from there, we use the AI techniques, so machine learning as what we call a pattern recognition from there. And we need to do the training of the data, and after that, do the classification. At the end, that's the way we use to predict an output linked to a particular application of the brain technology in here. Okay, that's a general block diagram how we do the AI and different kind of signal processing in a brain technology. Let's have a look in the first of the application. So we use the EEG for detecting what we call an hypoglycemia or low blood sugar. This is very important issue, which is for people having the diabetic. So, for example, the people have a, you can see here, when people have a diabetic, they have the insulin. During this, when they have a sleep, they tend to become dangerous as well, because they can, when they have the low blood sugar very low, and it can turn into the unconscious coma, even die as well. So that's how dangerous the hypoglycemia. Then you can see for different threshold that apply for the what they call low blood sugar. And this, we use the, to be safe, we use the last one here, less than 3.9 millimole per liter, that categorized into the hypoglycemia or low blood sugar. And some of the detection here, so for continuous detection, because you can see that you have to be invasive, they take a bath, they take a needle and measure the blood sugar, and which is inconvenient, because when you think about that during the sleep, we have to wake up all the time, check the blood to make sure our blood sugar is okay or not, which is very clunky and inconvenient as well. Then we do the research. This research is led by Professor Hung Nguyen. So he's currently is a pro vice chancellor at Swinburne University. I'm a part of the team to design a real-time system to make the hardware working. And we propose different methods. So you got a long research already in this area. He started with ECG, and now we try to move to the EEG as well for the hypoglycemia detection. So this hardware here is actually for the ECG detection. Now to do this one, we need the data. That's why we have to do the clinical experiment. We collaborate with the hospital to measure the hypoglycemia. So there's a T1 type 1 diabetic patient, and we do that 10 hours overnight hypoglycemia experiment. And there's a 5-stage in experiment, and on this presentation, I concentrate on the hypoglycemia only. And at the same time as well, we measure the blood sugar to validate the results, because that's important as well. We have to make sure that's below or on the bound or higher than the threshold of the hypo stuff. And for the EEG, because the purpose here we're using the brain technology, and we concentrate on using the EEG to collect the data. And that's the setting of the EEG. And we concentrate on the 4 channels. So occipital at the back of the brain there, and central cortex, which is the middle part of the brain. Because if we go back to the research review, we found out that's area that's playing important part of detecting of the low blood sugar. And as I mentioned earlier, in the AI, we have the features extraction process as well. So in here, one of the recent publication, we found out that in a certain high order spectral moment, it can be a good features for this kind of detection. And you can see this is algorithm of the spectral moment. I won't go that very detailed. You can have a look in the paper for this presentation. And this is the formula of different algorithm of the features extraction. For example, we use the combination of the centroid frequency and there's a spectral moment, what we call a duration radius, first derivative, second derivative of the things, the skewness. That's so we combine all the features together to become one's combined features for the classification at the end. And the machine learning, we use the standard neural network with the Bayesian optimization. So you can see this is the algorithm of the Bayesian algorithm. The Bayesian algorithm is quite interesting because we can find the optimal structure from there. It's still not a deep learning classification, but what we call a shallow kind of algorithm. But it's enough, I think, at the moment to classify that in this stage. And for the performance indicator, we use what we call a sensitivity. So sensitivity is like what we call a true positive rate. You can see by definition, it's like When you are hypo, classified correct as hypo, that's a true positive day. So the rate of true positive, what they call a sensitivity. And specificity is the true negative rate. So same thing is a non-hypo, classified as a non-hypo, that is a true negative. This is the result of the data. So you can see this is blood sugar, because we collect the blood sugar as well. You can see from the higher level of the glucose level in millimole per liter until they become hypo around that 3.9 millimole per liter. And this is the result. So first we check with the statistical. So whatever features that we propose, which we check whether in terms of statistics, is that makes sense or not? Is that significant or not? You can see some of them is quite significant. So I mean we can proceed further with the machine learning or the AI. And I forgot that one is on alpha band. EEG one, they have what we call a band. It's a frequency. We can convert it into a frequency analysis. This is a popular analysis in EEG. So they have the delta, alpha, delta, theta, alpha, beta. They have different frequency threshold. So alpha is around 8 to 13 hertz. So this is, we found that an alpha band have some significant features using this spectral moment, and also on theta band. So theta band is around 4 to 8 or 4 to 7 hertz on that one. So it's found some of the proposed of the features extraction have the significant there. And in terms of classification, you can see that's training. Training is we doing the process of the machine learning. So we train the data, and the result we concentrate on is on a testing set. So you can see at the moment the accuracy of, the sensitivity is at 82% with the specificity of the 51%. We published this paper already. You can have a look at this paper in 2019. And this is some of the publications. You can see the first name here is our PhD student. He's in final year to finish his PhD. And as I mentioned, before, Professor Hung is the main investigator for this research. And we are doing now to converting into the real time. So I'm designing the hardware now for the EEG and put the algorithm inside the chip. Okay, so that's first part of the application of the EEG. Let's move to the second one. Now, second one is my one of my main research, which is on driver fatigue classifications. Very interesting. It's very important issue in transportation. You can see that it's a major cause of accident in transportation. And some of the symptoms as a fatigue is, for example, when you're feeling tiredness, it can reduce the alertness and it decrease your reaction time when you're driving. So that's why it's very critical and danger if you have the fatigue symptoms. And because at the end you will lose the concentration and end up with a crash and accident as well. So in terms of statistics, you can see here in New South Wales and in Victoria as well. So in the fatal crashes of this percentage here is around that 15% caused by fatigue. And for the another statistic shown for Victoria and New South Wales, so top 2 or top 3 of the casual crashes is caused by something related with the fatigue. That's why driver fatigue is kind of interesting research that for me. So that's why I'm doing that research further. So it means that we need some sort of the automatic detection for this driver fatigue. So if you go with the literature review, there's some other kind of assessment you can use. For example, you can use a self-report using the psychometric questionnaires, which is inconvenient because you have to take the psychometric question. You can't make it automatic in that sense, isn't it? And we have to use other approach. So the other approach, we can use a physiological measurement. For example, we use a video recording. Some of the latest car actually have this video measurement for the driver fatigue, although they have some disadvantages as well. And they can measure by other biosensor, for example, the electrocardiogram, ECG, for measuring the heart signal. You can use to check your eye movement as well through the electro oncolography E or G. So when you blink or when you, so the certain blink rate, it can determine whether you fatigue or not. So we can have a look in that research paper. And our concentration is measuring by the brainwave. Okay. In order to do this one, this is same again. We use the same general structure as I mentioned before. So data collection is there. Some signal processing and AI need to be used in order to predict whether the fatigue or non-fatigue. So you can see the output of the detection here: fatigue or non-fatigue or alert. So in order, if you can detect that one, so as early as possible, is early detection is very important here. Then we can give alert in real-time situation to the driver. Okay. And we collect the data for this study. I collaborated with Sydney University, and they collect the data. So they collect using the EEG from the 43 participant driver with the EEG 32 channel. So you can see this is the data, the setting of the equipment. And this is how the signal looks like EEG, that 32 channel, and this is the location that we collected. Now this is, we're using the simulated driving. Of course, we can't use the real driving. It's quite dangerous. That's why because for this study purpose, in order to find a good AI to handle this driver fatigue, we use a simulated version. We need to make sure we have the alert data, and also we have enough data for the fatigue as well. And there's a simulated version, what they call DASS, Divided Attention Steering Simulator. That's from the scientific instrument. And the participant need to ensure that they doing that driving. They have to keep driving at the center. They have to make sure, you can see in here how that driving looks like. They have to make sure they keep in the center until we detect the sign of the fatigue. Then we stop that experiment. And some of the protocol here, how to stop the experiment, you can see when the fatigue is happen. For example, in terms of the facial sign there, if detecting as a fatigue, like nodding or extended of the eye closure, or if they driving and have the driving off the road for more than that 15 seconds, we stop them because that should be tend to be a fatigue. Otherwise, maximum 2 hours, we stop the experiment as well. Then after that, we need to validate because we need to make sure the data that we have enough data for, as I mentioned, data for the alert, non-fatigue, and data for the fatigue as well. Now to validate for the fatigue occurrence, first we use video monitoring because at the same time we measure the video, then we check one by one, oh, this is the fatigue condition of the data. And also we check as well for the performance experiments such as that deviation of the road as well. At the same time, we use that test, the psychometric test as well. So we have that, although it's biased to participant, but we combine all those of things. There's what they call a Chadol fatigue scale. So we make sure that scale is belong to the fatigue level, or what they call a sleepiness scale. Okay. Then we have data for the alert and fatigue. You can see we go through for the pre-processing because, as I mentioned earlier, the EEG tend to have a lot of noise. So, for example, when you blink your eyes, heart signal as well can be there. You move around your hand. It's kind of artifact can be detected in a EEG. So we don't want that artifact or noise in EEG in our signal processing. So we need to clean that one. So you can see here how I divide it into the segment, and then we use the algorithm to clean out the artifact. Okay. And again, same thing. Next is the features extractions. The popular features extraction for the EEG analysis, if you search in the publication, is what they call a frequency analysis. One of the frequency analysis is power spectral density. And this is the algorithm to calculate the power spectral density. And one of my publications, I actually found out that another algorithm called autoregressive modeling, so AR, have the good features for this kind of applications. So as I mentioned, EEG is not that easy in terms of the features. So different applications you found out different features can be used. So not one particular features is worth for one application, but for other application is not perfectly working and classified as what we want. That's why in this one of you can have a look in my publication on this driver fatigue. I compare and I found out that using AI is quite interesting and have a good result from there. This is the AR formula. And this is the composition data before we fit to the machine learning. Okay, so we use as well the previous conventional method of the PSD for the comparisons, and we use the features of the AR as well. And in terms of the machine learning, again, we use a standard neural network optimized by Bayesian software. So this is what they call a Bayesian neural network. And this is a theorem and algorithm of the Bayesian. Okay, and there's another publications I compare as well, and I propose deep learning. So in that publication, I propose what we call a sparse deep belief network. Deep belief network is part of the deep learning algorithm, and I found out that using this proposed deep learning method, it actually improved a lot in terms of the classifications. And this is the algorithm of the sparse DBN. Okay, and this is the structure of the deep learning that I propose. So compared to the Bayesian or standard neural networks, so deep learning have a different structure. So you can see you have what they call a generative structure, and they have the discriminative structure as well. So that's how they make it different compared to other shallow machine learning. So other shallow machine learning, they have only the discriminative platform, but deep learning, they have that combination. So in the generative, that one, they have the autoencoder try to find out the features themselves, and after that, they fit to the discriminative machine learning there. Okay, this is the whole structure of the sparse deep belief network of this paper. And the same for the performance measurement, we use what they call a sensitivity, specificity, and accuracy. So at the accuracy, so because we can calculate accuracy from the sensitivity and specificity as well. There. Okay, so this is the formula for that performance measurement that we're going to use for this study. And this is the result of the Bayesian, because as I mentioned earlier, so in a Bayesian, we can find the optimal structure. So the picture here show how the optimal structure, what's the hidden nodes of the artificial neural network, of the Bayesian neural network. So you can see on different features, so power spectral PSD, power spectral density of the features, they have the different hidden nodes, and also on the AR of the hidden nodes that to be the optimal one. Okay, and this is the result of the classification based on the Bayesian neural network on different features extraction. You can see here, in terms of the sensitivity is 84% there, specificity is 83%, and the total accuracy around that 83% as well. And next, another paper I propose using that sparse deep belief network. So if we talk about deep learning, people want to see how many layers is enough to classify. That's how that deep learning. That's make it different how that standard neural network compared to the deep learning. So standard neural network, they have problem to handle the higher layer of the training, but deep learning, they can do that one. But then when I compare actually that result of different layers of the proposed deep learning, it turned out that 2 layers is more than enough to do this kind of the driver fatigue data. So that's why I end up to choosing that 2 layer. You can see that comparison of the accuracy. The top one is still the 2 layer. So in that case, we don't have to be complicated to use more layers. Two layers of the deep learning is enough for our case. Okay, you can see the comparison between different features. The PSD and AR is there as well. And this is the result of the different type of deep learning and the one that we propose as well. This is on the power spectral density of the features. Okay, and in one of my paper, I actually propose AR as well. And with the deep learning, you can see it's increased to top to the 93% of the sensitivity, specificity of 92 and accuracy of 93. It's quite interesting. That's why at the moment we try to convert this one into real time, and we want to see whether is have the same thing in a real time situation. Okay, this is in terms of a statistical significance. We can see that a different comparison, they are significant of the proposed feature segregation and combined with the AI technique. This is latest publication as well. You can see a few paper with me as a first time, as a first investigator, and this is the latest paper, conference paper that we published. My PhD student, so I'm the principal professor for, this is Dulan Perella, and he analyzed another aspect of the driving, which is what we call distracted driving. Quite interesting. So he's just in his first year of PhD. So stay tuned. Hopefully we get more publication on this research as well on this experiment. And we collaborate this one with another professor from UTS, University of Technology Sydney. There's a professor from Taiwan as well. His name is Professor Siti Ling. He's a very famous professor, actually in AI as well. So we collaborate with him to do this driver distraction analysis. Okay, and if you check one of my paper, I just checked recently, since yesterday, still in a highly cited paper. So if you're in a web of science, one of my paper published in 2017, still in a highly cited paper. Quite interesting to see this paper have a high attention around the world, particularly on the driver fatigue detection. Okay. Again, as I mentioned you before, that in a way that doing that real-time testing. So we want to convert all the algorithm inside a real-time environment now. Okay, the last one. So check the time, 32. So we have time to. The third application of the EEG as a brain technology is one of my other main research. Actually, this is my PhD research. We talk about using the EEG for control the wheelchair. That's what we call it, a brain control wheelchair. It's very useful. You can see here when people have their disability, some of is in a lock-in syndrome. I will go that a little bit later. So in terms of the mobility, so for the people with disability, they use what they call a hands-free technology, isn't it? Some of the hands-free technology, for example, we call a sip and puff. So they have to sip and puff through the mouth to control the wheelchair. So which is very clunky as well, and it's not easy to use. And other things, they can use the voice control. So people with disability, they're able to talk, they can use the voice, but sometimes there's a voice issue, noise as well. The environment can be a problem. When you go outside, it's a very noisy environment, so it's not easy to use that voice control wheelchair on that outside environment. Some of them can use a muscle-based system as well, or head movement. We do have that research on this kind of the biosensor as well. But if you can see some of the particular disability, they are very disability. So a certain neurological condition, they can cause what they call a lock-in syndrome. It's a complete lock-in syndrome. So they can't use the hand, they can't walk, but the brain still function properly. So that's why we thought that we can use this brain, because the brain is function properly, to use as an alternative for this kind of control. Maybe this the only way we can use it, because the only function is the brain. So some of the disease, for example, the cervical spinal cord injury, or what they call tetraplegia, so ALS, amyotrophic lateral sclerosis, and brainstem stroke patient, they have those kind of condition. They are totally locked in. So the only one is the brain. Okay. So we propose to use this brain EEG one to control the wheelchair. And during that research, I actually collect myself this data. So we collect with normal persons and also people with disability as well. What we call a tetraplegia. So the level of disability you can see here from C3, C4, C5, C6 as well. So cervical is around that part of the area. So they can't move the hand, and that they can't walk as well. You can see some of they are on the wheelchair there as well. Okay, of course, because of this is a clinical study, we need to get ethics approval. So I do have the ethics approval there, and we measuring using the EEG. We concentrate on that particular channel. So because from the research review, those channels is play important part in terms of what they call a brain-computer interface. So central part of the brain, parietal, so at the back as well, just above the occipital area and the occipital channel as well. And this is how the protocol of experiment. Our concentration on this research, we use what we call a mental task. That's what we were going to do. We want to associate the mental task and certain control of the wheelchair. Okay. As the mental task is what one of them is a letter composing. So person just imagine they compose a letter in their head. We can use that one, for example, to turn the wheelchair to the left. Mental calculation, arithmetic calculation. So just think about the arithmetic calculation. Doesn't matter whether it's right or not. Just think about you calculate something in your head. So we want to detect that one using the AI, of course, and we want to use that one to move the wheelchair to the right. There's another one called Rubik cube rolling. So it's Rubik cube. You just imagined in your head that the Rubik cube rolling, and we want to associate that wheelchair moving forward. As additional tasks as well, the eye close data, because in EEG we know that eye close data have the dominant what we call an alpha band. That's why we use that one. And at the same time as well, we can use that one to, for example, another command to stop and to start the wheelchair. Okay, and you can see how that signal looks like in that experiment. Now next to after we done the signal processing, there's a features here as well. In one of my journal about this wheelchair control using the brain, I propose Hilbert-Huang transform for the features extraction. Again, the popular one is Fourier transform, the FFT, and I want to compare the one that I proposed whether is better or not. It turned out it's quite better. And the interesting part of the Hilbert-Huang transform is they can get the instantaneous frequency of that system and compared to the Fourier transform. That's why in terms of the features extraction, it's applied to different nature of the biomedical data. So EEG has the same scenario as well. They tend to be what they call a non-linear and non-stationary. So it's not that easy to get the features using the linear platform. For example, the FFT is sort of more linear. Then I go with that Hilbert-Huang transform so we can get the instantaneous frequency of the data. And again, this is the band of the EEG, the frequency band. So they have different bands from the delta, theta, alpha, beta bands there. And let's have a look at detail more of the HD. This is the algorithm. More detail you can have a look in the publication. And you can see here the idea of the Hilbert-Huang transform. We need to find the local extrema. From there, you can construct what they call upper and lower band of the envelope on the red line there. Then you compute the means of envelope, so on the green line. Then you check whether it's called IMF function, and you do this one repeatedly, so you can see until it become a what they call a monotomic signal. Okay, then you get the result of the Hilbert-Huang transform, the IMF. From there, we calculate the spectrum of the IMF. Then I test the algorithm on the eye close data. Remember that I collect the eye close data as well. And we have to make sure when we blink the eyes, when we close the eyes, we can see the domain alpha and domain the alpha bands. So alpha bands, as I mentioned earlier, is around 8 to 13 hertz. See on the red line here. So it's proof that using the Hilbert-Huang transform, we are still able to get the eye close alpha band there. Okay. Then we apply to the rest of the mental tasks using the same features extraction. On the publication on the published journal paper, on that time we proposed a new algorithm, a new optimization algorithm. The AI is still using the standard artificial neural network. What we optimize further using what they call a fuzzy particle swarm optimization. So if you're familiar with particle swarm optimization, actually they have a drawback there. So they tend to be easy to trap what they call a local optima, which is not very good for the machine learning. So we will stop the machine learning, but we will not generalize the problem yet, and we just suddenly stop. So that's what they call a local optima. There's a problem in using the particle swarm optimization when you apply to machine learning. And we propose new technique called this fuzzy particle swarm with that cross-mutated operation. So that fuzzy logic to optimize the parameter of the particle swarm. That's the idea. Okay. There's we found out that's become very interesting. It's improved a lot for the training of the AI of the artificial neural network. Okay. And we compare this one with the other optimization called genetic algorithm as well, and other kind of the machine learning. Again, still this is still using the shallow machine learning. At that time, we haven't used the deep learning yet. And this is the purpose of the optimization. You can see this is the pseudocode of the algorithm. You can have a look more detail in the publication later. As I mentioned, we use the fuzzy logic to optimize the parameter of the particle swarm optimization in order to train the neural network for our data. Okay, this is the optimal optimum data parameter that we have it at the end. And again, because we apply this one for wheelchair control, we want to see how quick it is. That's why we do the study on different kind of the segment, from 1 second until more than 1 second. I think in the result publication, I'll go with the 10 second. Let's have a look in the result section later on. So first we do that result on the eye close, because we know when we close our eyes, we should see that domain alpha band. And we prove that one using the proposed AI and features extraction as well. We can see high accuracy on eye close. So S is there's a S1 to S5 is the normal people, and T1 to T5 is people with disability, tetraplegia. We can see it's quite good detection of the eye close for them. We can use this one for another control as a stop and start command for the wheelchair. Okay, and this is the comparison of the algorithm. You can see between our proposed optimization technique compared to the other algorithm, genetic algorithm. Our proposed algorithm is outperform of the other one. And you can see for the time as well, because we can compare the time from 1 second to 10 seconds, how good it is, the classification. You can see at the 1 second is not that good actually from people with disability and with normal people, so 63 to 70 something %. But when we increase the time, we can see that it merged together. So which just makes sense. People with disabilities need more time to do that action, that control. And we end up the optimum one here, around 7 seconds, we can use for control the wheelchair with 83 or 80, above the 80% of the accuracy. So this is the comparison for different algorithm, the classifier as well. You can see the one that we propose with different kind of algorithm, features extraction. So at the end, we use that Hilbert one with that EEMD, what they call that. And we can see with the proposed machine learning, we can go up to the 80 something %, the one that we propose. Okay. So you can see the last one, that's the features extraction, and that's the machine learning. So 84% of the accuracy. This is the statistical analysis. We compare as well. In terms of statistical analysis, it makes sense. All of them is significant. Because for the real-time purpose, we want to check whether we can go below than that 6 channel, because you can imagine to wear that 6 channel on the head, which is very inconvenient. We want to see can we do it in 2 channel as well. That's why in the publication, I go further with a comparison different channel. I go with the 2 channel, and it's end out that on a certain channel, so which channel is contribute more. So O1 C4, so occipital and central, is contributes up to 80%. So you can compare 6 channel is 84%, 2 channel 80%. That's why we end up with a 2 channel for the real time. And I actually designed my own EEG as well for this case. You can see this is first version of EEG. So you can see in the clinical EEG, they need a gel. So that's what happened to the EEG at the moment. If you go to the hospital, they have to put EEG and they have to put the gel, which is very inconvenient for the real-time purpose for this kind of situation for controlling the wheelchair. So this is first version for the testing of to develop this EEG gel kind of system. And I moved to the dry electrode because we need a dry electrode in order to do that real-time system as well. So this is the proposed method of the dry electrode. I won't go detail of the design. If you need more explanation, you can send me email or ask questions further down. Or you can see in my publication as well. Some of the related publication actually explore more of this kind of design as well. And this is the embedded system. So because for the real time, we need a standalone device, which is we use an embedded system, a microcontroller. That's the one with the LED turn on there. It's an embedded system to control the wheelchair. And again, this is the EEG system that I developed. And we test the developed EEG. We have to make sure that's able to pick up the EEG signal. We prove that one we can, when we close our eyes, the system that I developed is able to pick the eye closed system, and we can see that signal is quite different between the eye open and eye closed. And you can see in terms of the frequency domains, 8 to 13 hertz, you can see the dominant alpha band there. And you can see when I use the system to detect the signal. And also, this is the another system in a publication we test. So in what we call a brain-computer interface, there's a different kind of the protocol as well. On one of the paper that I mentioned earlier, I used a mental task. We can also use what we call a steady-state evoked potential that needs a stimulus. So when we blink the LED on certain frequency, we actually can pick up that signal inside our brain using the EEG. So I'm going to prove the one that I developed are able to pick it up those frequencies as well. So one of the journal publication I actually addressed for this kind of signal. So this is the signal that I collected using the developed EEG. So they use to what we call a steady-state visual evoked potential. You can see on different frequency, I can pick it up from the brain. This is a frequency domain. So 6 hertz. So the LED turn on the 6 hertz, I can pick it up 6 hertz, 13 hertz, and 16 hertz. Okay. And I return back to test this one with the people with disability. So this is the real-time testing with that system. So that to see how good it is, they use that system in real time. And this is the real-time application. I think I have a video, quick video, controlling the wheelchair using a 2-channel dry electrode EEG. So you can see the white one there is the 2-channel EEG dry electrode, and I'm using the band on that using the strap on my head there to control the wheelchair. Okay. It's quite slow because we just want to test the algorithm. But you can imagine people with lock-in syndrome, they can't use the hand and foot. But if you can control the wheelchair by thought alone, that's very interesting as an alternative option. Okay, let me stop there. I think I stopped there already almost. That's the publication of just a journal and conference paper as well for this related project. And that's it for my presentation of that 3 application. As a summary, I just want to remind you back because this theme of this webinar is about the big data, is about the AI, is about the future of medical technology. I want to refresh you back again what we call industrial revolutions. You check again with long time ago when they start with Industry 1.0, when they having the steam energy, something like water and steam energy at the end of the 18th century. That's how they come up with different kind of the a product, the car powered by the steam and water, something like that. And go after that, there's Industrial 2.0, when they invent the electricity. That's we start our Industrial 2.0 at the 20th century. So you can see every equipment, car powered by electric. Even today, electricity is quite important role of our equipment. And then with the computer era, the Industry 3.0. So that's why you can see a lot of equipment until now. We use a microchip, we use embedded system. That's all computer thing. Same thing with the company as well. So they have a Microsoft, they have a IBM, they have the Apple. So every industrial revolution. So there's a lot of invention as the product there as well. Company will emerge from those kind of thing. And now we in the what we call Industry 4.0 is a cyber physical system. So for example, even in Asia, we use that what we call a big data, IoT, a little bit about the AI. So that's what's going on here. So in Indonesia, I believe you understand about the Gojek. So they use sort of the IoT platform for this. So that's part of the Industrial Revolution 4.0. So now the future here is going to be the Industry 5.0 is the era is like fully integrated AI. And also the human-machine interaction, human-machine interface is like how you communicate to machine, human to machine together. So this is the way it's conveyed in the future. It's very much linked to the theme of the presentation. I mean, seminar today. It's about the big data. It's about the AI. It's about the medtech, which is very fascinating. Okay, that's how I end up my presentation day. And last part is this is my contact. So if any interest, you want to collaborate with me, please go contact me. This is my contact there. And if you want a picture here, I'm using the EEG and control the WUSI. And my PhD student as well, my collaborator is there as well. Okay, thank you.
Okay, thank you very much, Pak Rifai. I always call him Pak Rifai because he came from Indonesia. He came from Indonesia too. Okay. Okay. And I think it's a Q&A time, and I'm going to read some questions from the chat. And the first one from Ms. Osmalina. Dear Dr. Rifai, it was nice to know that EEG also could monitor hypoglycemia besides brain activity. Because EEG is really complex signal, then how to overcome the possibility of the overlapping from the EEG application? I mean, how we could decide whether one EEG condition is hypoglycemia or in a fatigue condition.
That's why, as I mentioned here, in the process here, we need a data collection. So we get that data on that particular application. Then we decide from there what sort of signal processing further down. For example, the features we have to find what sort of features, because every application we found out that's different algorithm work on that particular data. So different features and AI technique as well. So even when I apply deep learning straight away to EEG, it's not working that straightforward. So we have to fine tune again what sort of features and the AI technique to make sure that have a good performance on that particular application. You can see when I present here, I have different features extraction and feature AI as well that work on that particular application. But hopefully, of course, in the future, we want to have the one general AI that work toward that application, but it's not working that way. Same thing with the features extraction as well on the what we call a natural data, isn't it? Ocean data, seismographic data, voice data. So at the moment, we can't find a good generalized features. There's still different features can be applied to those kind of things. Okay.
Okay.
Hopefully that can answer the question.
Okay. Let's move to the other questions from Mr. Firman Isma Serdana. Dear Dr. Rifai, for the fatigue condition monitoring, is it possible also to include other condition as well which may lead to accidents, such as being drunk or other health conditions?
It is possible. That's why at the end, one of my PhD students working on driver distraction. But because of for the research study, we have to be simplified. So we start one by one. Then after that, we try to find a way to combine those kind of things. So you can see in the publication day, one of my PhD students is in first year. We actually try to do driver distractions. So it's not fatigue only. So when you're driving, they have a lot of distraction. You can play the mobile, or you can imagine something. So that's what we call driver distraction. So that's different than fatigue. We want to see later on we can combine those things together or not. So there's a possibility, but in order to do that research, we have to start one by one. Then later on we can find a way to combine. Okay.
Okay. I think it's a really interesting question from Shifa Hasanah from BIAN Bandung Institute of Technology. And maybe it's my question too. If it's possible, do you mind to share the potential methods for that channel optimization or channel reduction of EEG and the reason behind it? Because I really amazed that you can control a wheelchair only with 2 channels of EEG, because it's really optimized. And how could we do it?
Yeah. Thank you for the question. That one is for the brain control wheelchair. So in that application, we use a mental task. So see, this is different application, different way to control. So if we use a mental task, if we go with a research review, what we call a brain computer interface researcher. So if we're using a mental task, think about the arithmetic calculation, letter composing. So in terms of the research review, we found out that a certain area of the brain is doing for that purpose. That's how we end up. Okay, why don't we choose only that particular local area? I mean, that's why we try to narrow down the sensor. Maybe we can use reduce the channel to determine that a mental task. But for different application, maybe different story. But for that wheelchair control, we can narrow down to 2 channel at the end that give the 80% of the accuracy in terms of the offline analysis. Mm-hmm.
Okay. Let's move to another question, Pak Rifai. From Alfian. Thank you, Dr. Rifai, for the presentation. I have a question about the implementation of this device. I mean, this device is referred to the all of your application maybe. How do you put all parts of the device to the users? Because I imagine it will be kind of a cap for the electrodes and the main box of electronic circuit around the body of the user. Maybe it's about the fatigue monitoring in the application in the application one, how to put the many sensors in the driver's body. Maybe it can make the driver inconvenient or something like that. Okay, verify.
Yeah, for the driver fatigues in the publication at the moment, I'm still going with 30 channel. Of course, later on we want to narrow down into a reduced channel, hopefully again 2 channel or less than something like more than like below than 10 channel. So then we have to in some of the product development, of course, we have to design a good like cap, something like that. So we have to collaborate with design graphics to design that in terms of the comfort, safety, something like that, and we can able to design a good product for that. So it's like a cap, something like that, and again, it should be a dry electrode. So we have to make sure the dry electrode is not hurting the head, something like that, and soft enough. That's why you can see one of my picture there. I have the dry electrode, which is very soft. So when you put on the head, we put a pressure, the electrode will spray that things, and in order to contact the head. So comfort is important when you go with the product development. So we can talk about that a little more when we have a really product development stage on that things. Okay.
Okay, and I think it's the last question for you, and in our webinar today, from Meirista Wulandari from Universitas Taruman Negara. Dear Dr. Rifai, how are you? It's very interesting about the video of real-time brain control wheelchair. I want to ask you about the sensor that you use in the real-time data acquisition. How fast did the data transmit and process from the sensor to control the wheelchair? Thank you.
Thank you for that. It's an interesting question for the EEG real-time control. You can see when we design an EEG, they have so in the setting as well, they have certain transfer rate. For example, I'm using a 256 hertz. So when you convert it into a second, so 1 divided by frequency is a time. So it's like in terms of millisecond. So that's how quick is we can receive the data from the system. So it's a millisecond. So then it's the same thing as well when we apply the signal processing until the next batch of the data coming. So still in a millisecond, we actually can apply that signal processing and AI then in that time period. And when you see in my publication, I do study in different time frame as well. So in terms of classification, so 1 second, 2 seconds, 3 seconds, 7 seconds, it turned out that 7 seconds is the best, but 1 second we still classify. The quickest one, we can even classify in millisecond, but of course the accuracy may not be that good. But 1 second, we can classify it up to that 7 seconds is enough to get a good accuracy. That's in order to do that real-time control. But of course, as I said, different second will have a lower accuracy than higher second on that particular application have the higher accuracy. So for the real-time application for using EEG only, it's no problem. It's in order to have the accurate classification, the AI to be put into that embedded system to improve the system. So we have to compromise that information. Okay, hopefully that answering the question.
Okay, I think we are come to the end of this session. Thank you very much, Pak Rifai, to give a wonderful presentation, amazing information about us, about the application of a brain-computer interface and artificial intelligence. And I'm sorry to the some participants that their questions I can't read their question. And if you have any questions, you can send email to the Dr. Rifai directly. Thank you very much, Pak Rifai, for your coming, and hopefully the presentation will give benefit for us. And thank you for your attention of all participants. And I over time to the MC. Thank you.
Yeah,
thank you, everyone.
Yeah. Thank you, Mr. Akib and Dr. Rifai Chai, from sharing such interesting knowledge with all of us. For the next, I would like to invite all of the participants to open the camera, and we will take a picture together. Please open the camera, and we will take the picture for the last session. Okay, from the page 1, are you ready? Okay, and then page 2. And then page 3. Page 4. Page 5. And then page 6. Okay. Excellencies, distinguished guest participants, ladies and gentlemen, we have had productive and inspiring time together, and this event about to come to the very end. I hope you found the presentation on this webinar are informative and helpful. Let us all be guided by all the things we have learned and heard throughout this event, and be able to see the influence our future. On behalf of Faculty of Science and Technology Universitas Airlangga, I would like to all once again thank you for joining this event. I wish you all have a pleasant day. My name is Osmalina. Thank you and see you in the next event. Good afternoon. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much.
Thank you, Dr. Rifai.
Thank you,
Thank you very
everyone.
much.
You, Pak Rifai.
See you.
See you again.
Thank you, everyone. All everyone.
Thank you.